IIT Delhi in 2001, and after that, again, just like Dr. Tyagi, I went to the US, earned my PhD, and since 2011, I have been a faculty at the University of Texas at Arlington, where I'm now a professor of mechanical and aerospace engineering, and it gives me great pleasure to bring this GIAN course to you all. So first of all, thank you Himanshu, Kulbhushan and all the other volunteers for putting this together. It does take a lot of hard work for them to organize everything. The fact that I'm able to just stand here and get started, there's a big foundation of a lot of hard work that has gone into bringing this to you over the last several months and years. So thank you so much for everything that you guys have done, and hopefully we'll have a very good time learning about something new, something interesting in the next 1 week or so. Okay, so as we get started, I just want to say that GIAN is it's a very loaded word. GIAN is a very complicated word to understand. What does GIAN mean? I think roughly speaking, in English, it probably translates to wisdom, right? And wisdom is a level that you reach after information, then knowledge, and then wisdom. Okay? I don't think I will be able to give you wisdom in this class. All I hope to do in this class is to give you information and maybe a little bit of knowledge. What you do with that information and knowledge depends on you all, and that is what will give you wisdom, which is GIAN, right? So hopefully this will be a good experience for you all to learn about a new field. Perhaps some of you are already working in the area of lithium-ion batteries. Perhaps you are curious about it, and I will start from scratch. I will start from the very basics, and I will not hopefully assume a lot of things, a lot of background information, and I hope I will build up to a stage where you can understand the main challenges, the main opportunities in this field, and then see how you are able to adapt it to whatever you are personally interested in. Okay, so please let this be a very informal class. I would welcome and I would be very happy to have lots of questions. That will really help me, because I don't like standing here and just talking on and on forever. It is very helpful if we have sort of a dialogue rather than a monologue. So towards that, please, at any point, do not hesitate to raise your hand and ask questions. I'm happy to take questions. It really helps take the lectures to an entirely different level. Okay, I'll start by just putting some of my information here. Here is my email address. And I am at the University of Texas at Arlington. I'm usually very quick on emails, so give it a try. I usually respond within an hour or two. All right. So let's get started. I will show you all the rough plan for this week. There may be some minor changes here and there, but roughly speaking, let's begin with discussing what to expect in the next several days. As I said, I will not assume a lot of background information. We will begin from scratch. So the first few lectures will be very introductory, and then as the week passes on, things will become a little more complicated, and my overall goal is to introduce you all to this research field and to be able to help you identify what are the key research questions to ask in the area of lithium-ion batteries, particularly in the area of heat transfer in lithium-ion batteries. So towards that, the first lecture, which is already on, is Introduction to Electrochemical Energy Storage, where I will give a brief introduction to what batteries are, what are they used for, what are the key challenges in batteries and so on. And then after a break, I will talk about the fundamentals of heat transfer. And then later on, a local faculty from IIT Ropar will talk about the electrochemistry side of batteries, where he will introduce the conservation laws for electrochemical modeling of lithium-ion batteries. And then at the end of the day, we will have a tutorial in which I will take up a couple of representative problems related to heat transfer, and I will solve some problems on the board. Tomorrow we will begin with a discussion of thermal challenges in batteries, and then I will talk about thermal modeling. Manish Agrawal will talk about P2D modeling for lithium-ion electrochemical modeling, and then as you can see, things get more and more deeper as the week passes on. All right, but today things will be sort of an introductory level before we make things more complicated. Okay, any questions so far? So before I get started, I just want to learn a little about the audience as well. So I'm assuming you all are here because you're interested in batteries and heat transfer. I want to know very briefly from each one of you what brought you here and what you hope to get from this GIAN course. Okay, so why don't we start from you?
Yes. Good morning, Professor. So it's glad to be at this GIAN course of lithium ion batteries. So myself, Dr. Arun, hailing from Coimbatore, Tamil Nadu, currently working as an assistant professor and head of the department physics at Summerville College of Technology, which is one of the top 100 NIRM institutions in the engineering category. Our majorly focus on nanostructured materials for environmental remediation, as well as green hydrogen generation using advanced oxidation process. We would like to move on, or we want to explore more possibilities towards batteries. Anyways, the world is moving towards the circular economy, sustainable world. Batteries will play a very important role. We also look forward to understand where are these batteries are moving on. Once the work has been completed, what is happening to it? It is again rendering as an e-waste. So how to manage that? So prior to understanding that, I'm not a battery related research person. So I just want to plunge in myself how these electrochemical batteries are working. I'm quite interested about the electrochemical impedance spectroscopy because we are having an experimental setup at our laboratory. We are working on it. The thing is that we just want to understand how the thermal phenomena will play a major role. Being statistics, we are responsible to understand how the phenomena are happening, which can build up into a major prototype and experimental modeling. And this will be quite new to you in understanding whether we can able to confine the heat transfer mechanisms in lithium-ion batteries, and we can extend its shelf life and the battery management system. Because we have a good student research run forum called Ray and Garage. They are participating in national and international tournaments. They are working on e-vehicles, development of renewable kind of things. So this would facilitate me to mentor them to make prosperous products.
Sounds good. Wonderful. Thank you. Thank you. Would you like to go next? Simply, what are you hoping to gain from this course?
My motivation to work in lithium-ion battery will start with you when you are given a half year. Currently, I'm working with the lithium-ion battery P2D model, so I want to explore more and a lot of the experimental side of it.
Sounds good. Sounds good. Good. Great. Sure. I see.
So that's why I'm eager to know what is this course and what I do.
Sounds good. Cool. I see. Great. Wonderful. Wonderful.
My work is on batteries, so I want to learn about this and I want to know about thermal electricity.
Sounds good.
So I am PhD student
I see. Sounds good. Great. Wonderful. All right. So I think we all have a common motivation of learning about batteries, thermal management, and so on and so forth. Let's get started. I want to talk about some very introductory stuff. Want to create a big picture motivation for what batteries are, where do they fit into our lives, and what is the importance of energy storage and so on. Right. So towards that, let's get going. Let me get to this, and I can go to the next page. So let's start by talking about energy storage. In fact, energy storage and conversion go hand in hand with each other. Before we even start talking about energy storage, however, let's make sure we understand what energy is. So what is energy? Energy is the capability of doing work, right? If any system has the capability of doing work, then we say that this system has energy, right? So for example, if I have a piece of coal, can this piece of coal do work? Remember, we also have a very specific definition for work. What does work mean? Work is being able to apply a force to be able to move a body, right? So if I have a body and if I'm able to apply a force on it and it's able to move a certain distance d, then the work done is force times distance, right? What are the units of force? Newton meter, right? And Newton meter is nothing but a joule. Okay, so if a body has the capability of moving something else a certain distance by applying force on it, we say that this body has energy. A piece of coal, does it have energy? It does, right? Because I can burn this piece of coal, convert the chemical energy of this coal into thermal energy, right? And the thermal energy has the capability of pushing something forward, like it happens in a steam engine, right? So a steam engine, you burn coal, you produce heat, which is used to convert to basically take liquid water and convert it into steam. That steam goes into a piston cylinder arrangement which pushes the piston forward, and ultimately we are able to convert the chemical energy locked inside the coal into a displacement work, right? So through this very simple example, you can see that there are a number of steps involved in converting the energy of this coal into work, right? I was not able to do it directly. I needed to convert the chemical energy of this coal to thermal energy. The other word for thermal energy is heat. So we converted the chemical energy of this coal to thermal energy, which is heat, right? Which was used to produce steam. So we converted liquid water into steam, right? And I'll talk a little more about this. That is roughly called latent energy. Being able to convert being able to convert liquid water into steam, we are basically providing it latent energy, which was then converted into displacement. So you can see that throughout this entire process, there were a number of energy conversion processes involved, right? If I just give you a piece of coal, you would think that it doesn't have any energy, whereas in fact it does have chemical energy locked inside it, inside the bonds in the coal, which if properly utilized can be converted into thermal energy, eventually converted into displacement. Okay, any questions on this? So this is energy conversion. The cousin of this is energy storage, and that the best example that I can give for that is, suppose you have hot water, or even better, what about steam? Suppose you have hot steam. You want to convert it to work. You can easily do that, right? How will you do it? You'll take the steam and you'll pass it into a piston cylinder arrangement, which will push the piston forward, and you would have created work. But suppose you decide that, look, I want to convert this energy into work, but I don't want to do it now. I want to do it 1 hour later, or I want to do it 1 day later, or I want to do it 1 year later. What would I do? Store it, exactly. I would need to store this energy in some mechanism which allows me to go back to it and say, now I'm ready to use that energy, give me that energy back. Okay, the simplest way to store it will be, okay, I take the steam and I put it in a container, seal it up, and then forget about it. I'll come back whenever I come, and hopefully that energy will still be there. Okay, as you can realize, I'm sure there's a big problem with that. The problem is that hot steam inside my cylinder will probably cool down as time passes, right? So if I have to come back to it a few minutes later, I will probably be okay. I may have gotten some losses, but the losses will be not so large. Maybe I'll lose a few percent of the energy in the steam. Most of it will still be there, and I'll be okay. But on the other hand, if I want to come back 1 week later, then this cylinder would probably have lost most of its energy to the surroundings, and I will not have hot steam anymore, right? So I need to think of what is the best way for me to store this energy so that I am able to come back to it without too much of a loss, and I'm able to tap into this energy later on, right? So energy conversion and storage go hand in hand. Does that make sense? So, how do we store energy? There are several mechanisms for storing energy, and I can list a few here. If I have energy, the easiest way to store energy is via sensible or latent heat. Sensible heat or latent heat. What does that mean? If I have energy, I can use it to heat up something. I can use it to boil water, right? I can take this energy that I have and I can convert water at 30 degrees Celsius to water at 80 degrees Celsius. And what would have happened is that this energy that I had is now stored inside the bonds in the water. And then if I keep this hot water in a cylinder, and if I insulate the cylinder well enough, then the energy would be stored there and I can come back and use it later. Right? This is called sensible heat. The word sensible means that there is no change of phase. This was a liquid here and it still is a liquid here. Can somebody tell me how much energy can I hope to store in water through this mechanism? Suppose I have 1 kilogram. Give me 1 second. Let me see if I can Okay, so my question is, if I have 1 kilogram of water, how much energy can I hope to store in this water if I heat it up from 30 degrees C to 80 degrees C? Does anybody know what that calculation is? Sorry? Exactly. The mass of this water, multiplied by its heat capacity multiplied by delta T is the total energy that I can store in this water going from 30 degrees C to 80 degrees C. Water is a very good medium for energy storage because water has extremely high heat capacity. Among most materials commonly available, water has among the highest heat capacities possible, and therefore water is a very good material for us to store sensible heat. If I keep going here and if I convert it to steam at 100 degrees Celsius, then I would have been able to store even more energy in the steam, right? How much energy is stored in the steam? It is mCp delta T plus m times L, where L is the latent heat of this phase change for water. In other words, I need to supply a certain amount of energy simply to convert liquid water into vapor form, and that energy needed to convert it from liquid to vapor form without any temperature rise is called the latent heat of water. Okay, this is probably the most common way in which we store energy. There are other mechanisms as well. So for example, there is thermochemical energy storage, in which the basic idea is that if I have some thermal energy available with me, then I will have a certain reaction occur which is an endothermic reaction. What does endothermic mean? It absorbs heat. It absorbs heat, right? So suppose there is some endothermic reaction that absorbs heat. I will carry out that reaction which will absorb this extra heat that I have, right? And that energy that I have will get locked into the bonds in B. Then later on, when I need that energy back, I will cause this reaction to occur in the opposite direction. In the opposite direction, this reaction is exothermic, which means that it releases energy. So when this reaction occurs in the opposite direction, that energy that I had provided to it will get released back to me. And if I am able to absorb that energy, I can use it for whatever reasons that I want, right? So as you can see, in any of these energy storage mechanisms, there is a certain efficiency involved. If I start from 100 joules of energy, and if I use it to convert A to B, I will probably not be able to capture all 100 joules of it inside B. Moreover, when B gets converted to A and it releases some energy, I will not be able to capture all of it. Some of it will go to losses here and there, right? So it is possible that I may have maybe a 2% loss going forward and a 2% loss coming back, which means that eventually the round trip efficiency will be around 4%. And as an engineer, is that acceptable to me? Am I willing to pay that price for being able to store that energy and use it later? Is the question that we need to understand. Yeah. Another way of storing energy is electrochemical. Which means that if I have if I have energy available in the form of electricity, I can use it to run a battery. I can use it to charge a battery. So I connect this to a battery so that this electrical energy available to me goes inside the battery, and we will go into more details of this shortly. There are certain electrochemical reactions that will happen inside the battery, because of which this battery will be able to absorb this voltage difference and store it inside the electrochemical bonds in the battery, so that in the future, if I have a load, an electrical load, and if I connect it to the battery, then this battery will be able to provide a current, and I will be able to do whatever I want here, produce heat, light up a bulb, run air conditioning, or whatever load that I may have. So this mechanism of converting electrical energy into chemical energy and then using it in the reverse direction is called electrochemical energy storage. So this is charge, I am charging my battery, and this is discharge. I am discharging my battery. Okay? It turns out that we often have electrical energy, excess electrical energy available to us. How? Imagine a power plant that is producing electricity, right? And that power plant is basically, it is meeting the needs of the electrical needs of a whole community, right? The electrical needs of the community will go up and down, right? People wake up, turn on the lights, start cooking, and the electrical needs go up, right? Then everybody leaves their homes, kids go to school, people go to work, etc. The electrical needs come down, right? Then in the night, everybody is running their air conditioning, right? Running television, washing machines, etc. The electrical load is very high. So the electrical load, if I was to plot the electrical demand or supply, let me use a different color for that. So let's do green for supply. As far as the demand is concerned, the demand is heavily, it goes up and down, right? So this peak is probably early morning, and then this may be the night, and so on and so forth. Whereas as a power plant engineer, I do not want my power plant to also do this in terms of supply, right? I don't want my equipment to change its RPM or its load in order to meet this demand exactly, right? That is not good for my equipment. As far as my equipment is concerned, I would very much like it to have a very steady load. So that my machines are working in steady state at the same RPM throughout, and it's not going up and down, right? What are two problems when my demand looks like this and my supply looks like this? Sorry? Yes, so some of it remains unutilized. So for most part of it, in fact, I am producing more electricity than I need. And what do I do with that electricity becomes an open question. And what is the other problem here? The other problem is that in these parts, I am not producing sufficient electricity to be able to meet the requirements of my community. Right? Those are two problems. And in fact, both of those problems can be solved if I can store this energy away. If this extra energy that I produce during most part of my day, if I can put it away, sort of like a fixed deposit or something like that, then I can encash it later on and meet the demands here. So that is, I hope you can connect this with this. I have extra energy available to me. I can use that energy I can convert it into chemical energy stored inside the battery, so that later on I can use the same battery and I can produce electrical energy back to me. Okay? Now, this discussion that we were having was sort of in the context of a traditional coal power plant, but it turns out that this problem of intermittency is also very common in renewable energy. What are some of the most common sources of renewable energy? Solar, yes, solar is the first one that comes to mind. So I have hot sun that is radiating a bunch of energy to earth. How do I convert solar energy into some useful form of energy for myself? Absolutely. There are at least two mechanisms of doing that. The first one is photovoltaic, which basically means that you take a solar cell. This solar energy falls on this cell, right? What happens inside this cell is called the photovoltaic effect, right? Which basically converts it into a electrical current. This is called photovoltaic effect. The other way to utilize solar energy is called uh, uh, concentrated CSP, concentrated solar plant. If I can go to a browser, I can show you a beautiful picture of a CSP. Here's a very beautiful picture of a concentrated solar plant. What is happening here is that we have a bunch of mirrors, literally hundreds and thousands of mirrors that are located in such a way that they all reflect the solar energy they receive onto a very concentrated region, right? You don't want to be standing here when this plant is running, right? You'll get roasted, literally, right? But if you have like a pipe, a network of pipes here that carries a heat transfer fluid, then all this energy can be concentrated onto that heat transfer fluid and it can be used to boil that fluid, right? I'm using the word heat transfer fluid because water is typically not used like this. Why? Because typically if you have so much energy coming onto here, water will boil, and when water boils it creates all kinds of problems. I don't want to go into that, but anyway, typically there are some other high temperature heat transfer fluids that are used for taking all this energy, concentrating it here and using it to heat up some heat transfer fluid. So I can have typically potassium nitrate or some such heavy salt which is used to take that salt from 30 degrees C to 600 degrees C, and then that salt is stored in some tank which can be used in the future. So imagine that I have early morning, the sun is shining, right? I can take this CSP plant and I can use it to heat up a lot of my working fluid, and then I can store it away and I can use it later. So during the day when the sun is shining, I can produce a lot of hot heat transfer fluid. And then in the night, when the sun is not there, the demand is still there, right? I cannot tell people, look, the sun is out and therefore I cannot provide you any electricity at this time, right? That's not going to work. That's not going to work for too long. And therefore, I can use this energy storage capability to be able to meet the demands of electricity in the future as well. If you think of it, almost all the sources of renewable energy have this problem of intermittency. Solar is one, right? The sun shines only 12 hours in a day, and then randomly there is a day that it's too cloudy and I cannot produce electricity. So if I have to convert into a solar based economy, I have to solve this problem. Other sources of renewable energy like wind also has the same problem, right? Sometimes it is windy and the wind turbines will rotate and produce a lot of electricity, and sometimes it's not windy. What do I do when it is not windy? Becomes a problem, right? So it turns out that the challenge of energy storage is very closely linked with renewable energy. We cannot possibly have a renewable energy based infrastructure unless we are able to solve the problem of energy storage. This was not such a big problem with traditional forms of energy conversion, because if I have a traditional coal based power plant, as the demand goes up and down, I can to some extent say, okay, let me burn more coal or less coal, and therefore I can produce more energy or less energy, right? But when it comes to the sun, if the sun is there, I can produce a lot of electricity, but if the sun is not there, I just cannot do anything. I can't tell the sun to come, right? That's not possible. That's not in my hands. So you can see that energy storage and conversion is very closely coupled with the question of renewable energy. Okay? So let's see. So I guess what I was trying to say here was, let's make a list of motivations for energy storage. The first motivation that we have discussed at length is renewable energy, which is intermittent. Where else in our lives do you think energy storage is important? Remote areas, absolutely. So remote use. There are many scenarios where I want to be able to use energy in a remote setting, right? I cannot produce a power plant or I cannot run wires everywhere, right? And you can think of this in two ways. One is in the context of a remote village, right? Say there is a village far away into the mountains where I need to use electricity. I cannot run wires there. Is there some way for me to store energy and take it there and be able to use it, right? The other is connected to all of us. Sustainability, absolutely. All of us, as we are walking around, we want our cell phones to work, right? I cannot possibly connect my cell phone by wire to the grid and then walk around, right? Otherwise, there'll be a wire following me everywhere I go. That's not possible. And therefore, in order to run my cell phone, I want to be able to have a source of energy where energy is stored, and I can take it with me wherever I go, and I can tap into it whenever I want to check my email or play a game or whatever else it is, right? That is the reason why our cell phone comes with a battery. That battery is basically storing that energy. If I go back one slide before, you see when I go back to my room and I have access to an electrical outlet, I use that electrical outlet to charge my battery, my cell phone, right? And then as I am going out and about, that battery is available to me to run my cell phone, right? So it makes it very convenient for me. That's another motivation for energy storage. And in remote use, I would like to say including space. This is a very important consideration, because if I have a space mission going into the space, to the moon, to the Mars, wherever, there is no energy, no ready source of energy available there, right? So my spacecraft needs to carry its own energy with it, and for that I need to store energy in some form that is easy for us to take with us wherever we are going, whether it is, out for a walk or it is into space. Any other motivations for energy storage that anyone can think of?
Safe utility.
Sure, safe utility, absolutely. For safety. I can always say that, look, I can take the example of space, right? I can always say, okay, why don't we take some coal and we'll burn it out there and we'll produce electricity as we go, right? That is obviously not possible for many reasons. I cannot burn coal. Even if I was to able to burn coal, it would not be very safe, right? There are several problems with that very crazy idea, right? So instead of that, I want to be able to have some other safer mechanism for me to take my energy wherever I want to go, right? So these are some main motivations for me to be able to store energy in some mechanism. Of course, the motivation for our class will focus on electrochemical energy storage, even though I listed several other mechanisms. We will now zoom into electrochemical energy storage specifically. Okay? Before I start talking about what a battery is, what it looks like, and so on and so forth, I do want to talk about performance parameters of energy storage. In other words, if I have multiple candidates for energy storage, how do I evaluate each one of them against themselves? What are their characteristics that I would be looking for? What are some desirable features in the energy storage mechanism that I would like to have? Is the question I'm asking, right? Let us think of this in the context of a cell phone. So here is my cell phone. This cell phone has a battery inside it. What are some features of the battery that I look for in buying my cell phone?
Charging, discharging, time.
Time, sure. So actually even before that, even sure, weight and volume.
Surface volume, how it is.
How heavy is it and how much space it occupies, right? It's a very important consideration. It's a very practical consideration, right? If I buy a laptop, the first thing I want is it needs to be light so that I can take it everywhere and I can carry. Hi, how are you? AC ठीक चल रहा है? Is the air conditioning okay? Sure? जी ठीक चल रहा है बढ़िया है। हम लोग बताते हैं अगर कुछ होता है तो। Thank you जी। So we always look for a lightweight battery, right? Can you think of what are the units of this performance parameter? that I would be looking for. Suppose I give you two batteries, battery A and battery B, and if I look at the spec sheet, how will this consideration of weight be captured in the battery? Energy density, which has units of? Yes, you all are on the right track. So it would be how many joules I can store per kilogram, right? In 1 kilogram of this battery, how many joules of energy can I store? By the way, instead of joules, I can express it in the form of watt hours per kilogram, or as you were saying, amp hours per kilogram at a certain voltage. So if I have two batteries, one has, 2 watt hours per kilogram versus 200 watt hours per kilogram, the 200 watt hours per kilogram battery is able to store much more energy in it per kilogram of its weight, and therefore would be desirable. Volume is another important consideration, because um, I don't want my cell phone, I mean, we all want small phones, right? Phones have become smaller and smaller. In the early 2000s, when the cell phones first came, if anybody remembers, it used to be like a brick. It was literally as heavy as a brick and as big as a brick, right? It has become smaller and smaller. It turns out that it has been very easy for people to miniaturize electronics. Electronics can be made smaller and smaller. It is battery technology that took a very long time to become smaller and smaller. So it is the batteries that often limit the size of a device such as a cell phone. Even today, even today, the battery of a cell phone is a considerable percentage of its volume. Roughly what percentage of the cell phone is the volume of the battery? Percentage in terms of volume? 15 to 20% is probably a good guess, right? So a big chunk of your battery is just, sorry, a big chunk of your cell phone is just the battery. And I think the same goes for a laptop as well. Perhaps in a laptop that percentage is even larger. A battery is a very large sized system, right? So oftentimes this is an important consideration. When you go to space or in an aircraft, this is extremely important, right? Every kilogram extra weight on a spacecraft makes a very big difference in how far it can go, in what kinds of things it can do, and so on and so forth. So people who work for space companies are extremely paranoid about how heavy each of their components are. And people who work on space batteries are forever trying to reduce the weight of their battery, right? So this is energy storage density. What else would I be looking for as I go looking to buy a battery? We've said joules per kilogram or watt hours per kilogram. What else is important for me? Sorry?
Should be long lasting.
Should be long lasting, sure. But before these qualitative characteristics, I want to introduce one more characteristic, which is called an energy discharge density. Sometimes it's just called energy density. And the idea there is how many watts of output can I get per kilogram. This is different from watt hours per kilogram. Watt hours per kilogram was how much is my storage capability, how much energy can I store, right? What I'm asking here is how much energy can I release per kilogram. Why is this important? This is important because there are some applications that require a lot of energy, right? When I play a game on my cell phone, it probably does not require a lot of energy, right? So just a few watts per kilogram will be sufficient for it. But there are other applications in which I want a lot of energy coming out of my battery. For example, in some military applications, what they want to do is they want to have a battery bank. Oops. That has a bunch of batteries, and there is a dead weight in, it's just a dead weight. I want to take this battery bank and I want to use it to hurl it far away. So imagine I'm on a ship, I'm fighting a war, right? And what I'm doing is that I will take this dead weight and I will throw it away at a very high speed, right? Like a cannon. And for that I need a lot of energy coming out of this so that I can push it as fast as I can, right? So that this can go to the enemy's ship and it can hit it at such a high speed that it creates a hole and the enemy's ship goes down and all that stuff, right? In order to do that, I need two things. I need this battery bank to be able to store a lot of energy, which was my first characteristic, and also when the time comes, when the time comes, it has to be able to discharge a very large amount of energy in a very short amount of time, which is watts, right? A watt is a joule per second. So I want to be able to release a lot of energy per second in order to be able to do my job. Do you see what I'm saying? To give you a very simple analogy, here is a bucket. A bucket with a hole, I guess. Oops. let me just draw it again. Here is a bucket with a hole in it. How much water this bucket can store is related to the first characteristic, the energy storage density. How much water can I store in it, right? And then if I open this valve, what is the rate at which I can get water out of this bucket is the second characteristic. And both are important. In some applications, the first one may be more important, and in some applications, the second one may be more important. It depends on what you're looking to do. There are certain batteries which are very good at storing a lot of energy, but are not very good at being able to release a lot of energy. On the other hand, there are other batteries that may not store a lot of energy, but when required, they're able to release it at a very high rate. So you have to match your battery to the characteristics of the application that you desire out of it. Sometimes you want a lot of energy, and sometimes you just want a lot of rate of energy release. Other characteristics include cyclability. Cyclability means that I want to be able to do this again and again and again. If this battery bank will only allow me to fire once, then what's the big deal, right? I will probably lose the war. Similarly, in my cell phone, if I am able to use it only for one cycle, then I'll have to go buy a cell phone every other day, right? I want to be able to go back to my home and be able to charge it for the next day and for the next day, and I want to be able to do it again and again and again for hundreds or thousands of cycles. Whether my battery is able to cycle or not is an important characteristic of the battery. Some batteries have very good energy storage density, are able to release a lot of energy when I want, but they are not good at being cyclable. They are a one-time use battery, for example. In fact, there are two types of batteries. One is called a primary battery, which basically means that it is not cyclable at all. I go buy it, it has some energy stored in it, I will use it. Once I have used up all the energy, I have to throw it away. Right? The other type is called a secondary battery. Which is able to charge and discharge. Okay? Uh, and there I have the ability to go back and forth between charging and discharging. But even there is a certain limit to how many times I can do that. Every time I charge and discharge the battery, it will undergo some wear and tear. Again, going back to the example of a bucket, I can take a bucket, I can fill it up with water, take a bath, the next day I can again fill it up, take a bath, I can do it a large number of times, but eventually this process will cause wear and tear in the battery, in the bucket, right? And eventually it will, it'll go wrong. Something will go wrong with the battery, the material will deteriorate, and it will no longer be able to store water for me. Right? Exactly the same thing happens in a battery. Every time we charge it and discharge it, a little bit of it deteriorates, some decomposition happens inside the battery. And if I do it enough number of times, then eventually the battery will lose its performance characteristics, and at some point it will not be feasible to use it any longer. Right? How many of you have seen that in your cell phones? Right? It happens all the time. When I buy a new cell phone, I'm able to run it almost 2 days before I have to charge it again. Right? But a 1-year-old cell phone, I have to take a power bank and walk with it everywhere, and after 3 or 4 years, it literally cannot hold any more energy. That is sort of like this bucket getting so frayed and damaged that I can no longer fill it up with water. A bucket and a battery are very similar to each other. Okay? So in the coming lectures, we will talk about this very much. We will talk about what goes wrong in a battery as you cycle it, and what are the ways to prevent it, and so on and so forth. And we will learn that heat transfer plays a very important role in that process. Okay? Any questions or comments so far? Yes. Yes. So a primary battery is one that does not, there is no charge or discharge possible. Exactly. So the most common example of a primary battery is a AA or a AAA cell. I go buy it, I put it inside a toy that my son plays with, right? And when it completely discharges, then I have to take it out and put another battery there and throw that one away. That is called a primary battery. A secondary battery is one that I can charge, discharge again and again and again, like the battery in a cell phone or in an electric car, an electric scooter, and so on. That is what is known as a secondary battery. Okay? Any other questions or comments here? As I said, please feel free to ask questions. Don't feel shy. It's a small class. I will not mind any kinds of questions at all. I'm very happy to get questions, and it really helps focus on the important things here, and so on and so forth. By the way, this field that you all are interested in is a very noble field, no pun intended, because the person who invented lithium-ion batteries won the Nobel Prize for it, right? John Goodenough. In fact, I want to brag a little bit because I have had the pleasure of meeting John Goodenough. I'll see if I can If I can find I'll do it during the break perhaps. This will take a little bit of time. So let me go back to where we were. But in 2016 or so, I visited the University of Texas at Austin where he was, and of course I wanted to meet him. So I sent him an email saying, Dr. Goodenough, I will be visiting and I want to meet you. Would you be available? At that time, the guy was 96 years old. Within an hour, he responds, says, "Hi, Dr. Jain, I'll be very happy to meet you. However, I have meetings from 9 o'clock to 5 o'clock all day." 96-year-old guy, he's busy in meetings all day, right? Can you please come at 8 o'clock? And I said, yes, sure, absolutely. So I walked into his office at 8 o'clock, and he was the most energetic person, no pun intended, that I have ever met. You know, giggling and gaggling and happy to talk and, you know, discussing all kinds of things under the sun. And then at about 8:40, his administrator, his secretary walks in and says, would you like to take a picture with him? And I said, yes, of course. And so I have that picture. I'll show it to you all just as a way to brag about. You know, I think that was, that is my closest, that is the closest that I have come to winning the Nobel Prize myself. To be able to touch and shake hands with somebody who actually did win the Nobel Prize. At any rate, the point I'm making is that the possibilities are endless here. Even if you don't actually win a Nobel Prize in lithium-ion batteries, perhaps at the least you can make a very good career out of it. And you can ask some very good questions and get a PhD and all that good stuff. Okay? So I think we are all on the right track. Let's start talking very briefly about what a battery looks like. Batteries, by the way, are not a recent phenomena. The first battery was discovered by a guy called Volta hundreds of years ago. I forget the exact date, but at least 300 years ago or something like that, right? What a battery is a cathode it's an anode and a cathode. In the anode, now I can use a lot of colors, so let's do this. I have a copper bar, okay, in a solvent that has copper ions in it, okay. On the cathode side, I have a silver bar suspended in a fluid that has Ag plus silver ions in it. If I connect these two externally through a wire, and a switch, and if I provide what is known as a salt bridge, then what will happen on the anode side is that this copper will produce copper plus or copper 2 plus 2 electrons, okay, and on the cathode side copper 2 plus. On the cathode side, the silver plus and the electron will produce silver. The electrons are transferred from the copper side to the silver side. Okay. Anode, this is what is known as an oxidation reaction. Oxidation is the loss of electrons. So copper is losing electrons and oxidation is occurring on the anode side. These electrons are passing through. Of course, I need to close this circuit. They will go on the silver side where these electrons will be used up to convert silver ions into solid silver, into metallic silver, right? And this process from an electrochemical point of view produces a potential difference which I can use to run a load, right? So if there's a light bulb here, a bulb, that bulb will light up as soon as I press this switch down, because on the anode side I will be producing electrons. These electrons are passing through to the cathode side where they are used up to produce silver, and during this process these electrons will pass through the bulb and the bulb will light up. This is an example of a very simple example of a battery. Roughly speaking, this is what Volta had discovered hundreds of years ago, and this process will keep going on until all of this copper gets consumed. But once this copper gets consumed, then this reaction will stop, because there's nothing else that we can do. All of this copper is now available in ion form in the solution. It is not possible for me to convert this back into the copper, at least in this very simple example, and that is why what I have drawn here is a primary battery, right? Once it stops working, once all of this copper is used up, then there is no more battery available to me. And this is roughly what happens in a AA battery. The AA battery that we purchase has roughly this structure. It's not aqueous, of course, it's not liquid, right? But roughly the same reactions sort of happen there. And once I consume all my copper, then there is no more energy that I can produce from here. Over the years, this very simple construction has become more and more complicated with many other electrochemical reactions in addition to this very simple one, and each of those have produced newer and newer, more and more complicated types of batteries, including the capability to cycle it. See, in principle, once all of this copper has been converted into copper 2+, if it is possible for me to run the reverse reaction, then it becomes a secondary battery, and I'm able to charge it, discharge it, charge it, discharge it hundreds or thousands of times. And that is exactly what happens in a cell phone battery, right? Or even taking another example, in the 12-volt car battery. In a regular IC engine car, there is a 12-volt battery that stores energy to be able to start the car, right? And as the car then begins to run, it charges the battery back. In the 12-volt battery also, there are similar chemical reactions happening. It is typically based on lead acid. So it has lead in it and it has H2SO4 in it. I don't remember the chemical reactions that happen in the lead acid battery, but they are similar. You produce electrons on one side, you consume electrons on the other side, and that is what helps you run the battery. I thought I had my water bottle. Oh yeah, yeah, yeah. This is what I was looking for. And in a lithium ion battery, which will be the focus of a lot of our work, the reactions are somewhat more complicated. Let me just refer to my notes. I want to make sure I get this right. There is the anode side, and then there is the cathode side. Typically, the working material in a lithium ion battery is a lithium salt, such as LiMNO2, or lithium iron phosphate, PO4, and so on. There is a whole world of material scientists, chemists, who worry about these chemistries and who come up with the right material which will satisfy all of those requirements that we talked about a few slides ago. Right? So the chemists are worrying about what are the right chemistries, structural at the level of atoms and molecules. How do I arrange these atoms and molecules in a way that they're able to store the highest energy or produce the highest energy rate, and so on and so forth. That's not my expertise by any means, and you know, it was people like John Goodenough who came up with these materials. Let me just take a look at my notes, and I'll put down those equations. So on the anode side, we have lithium, some compound of lithium and carbon, which gives me C6 lithium ions and an electron, and this is during the discharge process. So during discharge, on one side of the battery, I produce lithium ions and electrons. So let me just draw a very vague picture of this here. I have the anode on one side, I have the cathode on the other side. These are connected to each other externally. Okay, so during the discharge process, this reaction happens on the anode side, which produces electrons. The electrons go through the outer circuit and they reach the cathode, and on the cathode side, the reaction that happens is cobalt oxide plus lithium and electrons produces lithium cobalt oxide. The ions, the electrons are passing through externally. The lithium ions are passing through the electrolyte. This is called the electrolyte. And they're reaching the other side where they will intercalate. This reaction is also called intercalation. Basically, the lithium combines with the electrons and produces the lithium salt, lithium cobalt oxide, which gets deposited on the cathode side. Remember that anode is where the oxidation happens. Oxidation is the loss of electrons, right? If you cannot remember it, oil rig. Oxidation is loss, reduction is gain. of electrons. Okay, so I hope you will never forget it again. Oil rig. One practical consideration there is that the electrons that I want to pass externally can also pass through the electrolyte, and if that happens, it's a short. So practically speaking, here there is also another component called the separator. This separator is a material which has the capability of letting lithium ions pass through it, but the electrons don't pass. The electrons only have a choice of passing externally, and therefore the separator plays a very important role of not allowing a short to happen between the anode and the cathode. So roughly speaking, this is what a lithium ion cell will look like. The reactions that I have written are for discharge. So during discharge on the anode side, I produce lithium ions and electrons. They both move to the other side and they allow the lithium to intercalate into the lithium cobalt oxide. Then, yes, intercalation basically means this reaction that produces lithium cobalt oxide. Sorry? Yes, correct. And the opposite reaction will be called de-intercalation. During the charging process. So during the charging process, this entire thing will work in a reverse fashion. So this becomes the anode and the reaction happens in the opposite direction, and this becomes the cathode and the reaction happens in the opposite direction. And the good thing about the lithium ion cell is that it has the capability of going either ways, depending on whether I have a load or an energy source available to me. If instead of this load I had, you see, this is discharge. This load, when I attach a load, it will discharge, but if I attach energy source to it, then that will cause it to charge. And that is indeed the good thing about a lithium ion cell. It has the capability of charging and discharging hundreds, thousands of times. That is the reason why we are able to build electric cars on lithium ion cells. Because I don't want my electric car to only charge once. I want it to be able to charge it. How many times do you think an electric car should be able to charge and discharge? Let's do a quick calculation. If I buy a car, how long do I expect to have the car?
5 to 7 months.
5 to 7
Yes.
years, sure. Maybe even longer, maybe 10 years, right?
When
Huh?
it does not change, people expect to change the cars frequently.
Is that right? Okay, I'm a little more conservative. I want to run my car for,
Minimalist as well as
sure, fair enough, fair enough. In about 10 years, other parts of the car will also break down.
yes, here and here.
Wear and tear will happen, and eventually I'll have to dispose of the car. But the battery itself needs to be able to run for, let's say, 10 years. And I want to be able to charge and discharge my car every day, right? Or maybe every 2 days. So if I divide this by 2, that's around 2000 cycles. Right? This means that I want to be able to charge and discharge my car at least 2000 times. What about my cell phone? I want to charge it every day, right? How long does a cell phone last? Few years, maybe 2 years, right? People want to change their cell phones all the time, right? And the battery is the first thing that probably dies. It gets so bad to charge a cell phone that I want to just buy a new one, right? 2 years, that also comes to about the same. that is also 2000, 4000 cycles. So that is roughly what people are looking at. I want a cyclability of at least 2000 to 4000 cycles. Okay? In this process, in this very simple process, there are a number of heat transfer phenomena that occur, which is of key interest to our GIAN course. We want to look at this simple electrochemical system in the context of heat transfer. How does heat transfer, energy, etc., thermodynamics affect this process, either positively or negatively, and how do I design this system in order to take advantage of thermodynamics, in order to stay within the laws of thermodynamics, and in order to minimize the damage that thermodynamics can do to the cyclability of this system. So in the coming lectures, that is what we will specifically focus on. Our focus in this class will not be necessarily on the electrochemistry of it, but rather on heat transfer and how heat transfer and electrochemistry interact with each other. So towards that, just to give you an overview, in the next lecture, I will talk about some fundamental principles of heat transfer, especially for the benefit of those who have perhaps never taken a heat transfer class before. How many of you have not taken a heat transfer class before? Don't feel shy, that's quite okay. Yes, so for the benefit of those who don't have a good background in heat transfer, I will summarize the principles of heat transfer in the next lecture. We will have a faculty from IIT Ropar go into the details of the electrochemistry of the cell, because that is also important for us to know. What I have taught here is very basic, very fundamental, but we'll have the benefit of an expert going into the details of the electrochemistry as well. And then tomorrow we will start talking about what are the different ways in which heat transfer affects the working of a lithium ion cell. In other words, what are the thermal related challenges in a lithium ion cell? That's what we will do tomorrow, and slowly we will warm up, no pun intended, and go deeper and deeper into the heat transfer aspects of a lithium ion cell. Okay, so are we okay to take a break now? Sure. So let's take a break and be back at 30 minutes. So we'll take a 30 minutes break. Don't wander too far away, and we'll meet again in 30 minutes to talk about some fundamental principles of heat transfer. All right. Thank you so much. Let's see. Alright, so let's get started. This is the second lecture of our GIAN course. In the first lecture, I provided a very broad overview of energy storage, and then we looked at electrochemical energy storage in particular. And I said that we will be focusing on heat transfer aspects related to electrochemistry. And so I think it's a good idea at this point to look at some fundamentals of heat transfer itself, right? So in this lecture, we will not talk about batteries as much. I want to lay down some fundamental principles of heat transfer so that in the coming lectures we can integrate the two, batteries on one side and heat transfer on the other side. So in this lecture, we talk about what heat transfer is, how does heat flow, what are the various mechanisms and equations that govern the flow of heat, and so on and so forth, right? So let's start with a very simple example. Suppose I have hot tea. I take this hot tea and I keep it out on a table. What happens to this hot tea as time passes?
It's cold.
It gets colder. Clearly, it gets colder. Or instead of a hot tea, if I have a hot metal ball, this metal ball has just come out of the oven, some manufacturing process, right? I lay it down, and as time passes, its energy goes down, right? How do I characterize its energy? What is different between this hot tea and the tea after some time, which has now become cold? How do I tell that this is hot tea and this is cold tea? Temperature, exactly. So the temperature, T, is the quantity that characterizes the content of energy in this body, right? It's like a measuring tape. Whether something is very long or very short depends on how it scales, right? How does it measure using a scale? And similarly, the energy content of this body, any body, is characterized by its temperature. The higher the temperature, the higher is the amount of energy in that body, right? I can measure temperature in many different ways. The simplest way is, how do I simply measure the temperature of this tea? Put my finger in it, right? If I put my finger in it, my finger will immediately know if it is hot or cold. And there are many other ways of measuring temperature, which we will look at perhaps on Thursday. But for now, all I want you to know is that temperature is the characteristic quantity that governs the energy content of the body. The higher the temperature, it means that the greater is the energy content in the body. And if I have a body at a high temperature, suppose I have a hot body, and by now you know that hot means high temperature, right? And suppose there is another body which is cold. And suppose I get them in contact with each other. What will happen?
Heat exchange
Heat exchange will happen. Heat will flow
from hot into cold.
from hot to the cold side. So that the temperature of the hot body goes down, the temperature of the cold body goes up until the two temperatures become equal to each other. So if I was to plot temperature versus time, the hot body temperature will probably look like this, the cold body temperature will probably look like this, until the two of them are almost the same with each other. This process is called heat transfer. the flow of heat. I'm using the word flow as if it's a liquid. We use the word flow typically with liquids, right? We also use the word flow with heat because heat in many ways behaves like a fluid. It's really not a fluid, clearly. Historically speaking, in fact, 200-300 years ago, people like Fourier, etc., when they first discovered heat and the flow of heat, for some time it was believed that heat is actually, in fact, a fluid that we cannot see with our eyes. A hot body has a lot of that fluid, a cold body doesn't have a lot of that fluid. If you connect the two, the fluid will flow from the hot body to the cold body, just like a bucket. A bucket is becoming our good friend here. If I have two buckets, and if this bucket has a lot of fluid, and if this bucket doesn't have a lot of fluid, and if I connect the two buckets, what will happen? The fluid in the bigger bucket that has a lot more fluid will flow into the bucket that doesn't have a lot of fluid until both of them have the same level, right? This is exactly the same way heat flows as well. The hot body that has a lot of heat will transfer its heat to the cold body that doesn't have a lot of heat until the energy content of the two become equal to each other. So you can see that the flow of heat and the flow of fluids are actually very similar to each other. In fact, we will learn that the equations that govern heat flow are actually very similar to the equations that govern the flow of fluids. Yes? Any effect on the? Yes. In this case, there is a transfer of mass, right? But here, there is no effect on the mass. As heat flows from the hot body to the cold body, it does not carry mass with it. The weight of the hot body and the weight of the cold body will remain the same. Sorry? The density will not change here. There is no transfer of mass that occurs. Only heat flows. But mass does not flow, at least in this simple example. Do you see what I'm saying? Do you understand what I'm saying? Cool. The flow of heat must govern several fundamental laws of physics. If I just have a hot body and if I just have a cold body, there will not necessarily be transfer of heat from one to the other. First of all, there must be a connection between the two, right? Secondly, there must be a temperature difference between the two in order for the heat to flow by itself, right? If I have a cold body and a hot body, heat does not flow from the cold body to the hot body spontaneously, right? A glass of water sitting here will not by itself become hotter and cool down the room. I wish it could happen, but it does not happen, right? There are fundamental laws of thermodynamics that heat transfer must obey. The first law of thermodynamics is that energy must be conserved, which means that if 100 joules of heat leaves the hot body, then barring any losses, leakage, etc., exactly 100 joules of heat must be gained by the cold body. I cannot create or destroy energy. That's the first principle of thermodynamics, and heat transfer processes must satisfy the first law. Question? Yes, it will, and if yes, the volume might change. Yes, sure. We are neglecting those effects here.
That's what we call as thermal expansion.
That is what is called thermal expansion or contraction, but we are not worrying about that right now. Those are minor effects. Yes, in that sense, you're absolutely right. The density might change, but there is no bulk motion of the mass. It's not like the hot body will lose its mass as well. Okay?
Transfer of heat takes place to the nearest neighboring atom which can conduct it.
Yes, absolutely. So the first law says that whatever heat is lost by the hot body must be gained by the cold body, and I cannot by myself create or destroy energy. The second law, which in some ways is much more interesting, talks about the spontaneity of this process. Roughly speaking, it means that if I have a hot body and a cold body and I connect the two to each other, then heat will always flow spontaneously from the hot body to the cold body and not the other way around, right? And that is indeed our usual experience. If I bring a cup of coffee and if I put it down here, the coffee will cool down, the room will heat up at the expense of the coffee, and all of this will happen naturally, spontaneously. That is how nature wants it to happen, right? But now we come into this picture, and there are so many occasions and systems around us where we want to go against the will of nature. I have this room, I have the outside. On a day like this, the outside is very hot, the room at the start of the day will be cool, right? If I do nothing, what will happen as the day passes? This room will heat up because of the heat outside, right? But we want it to happen the other way around, right? For our own comfort, we want to remove heat from the cold body, the room, and reject it to the hot body, right? Sink to source rather than source to sink, right? And the same thing happens in a refrigerator. I take a bottle of water, I want to cool it down, I stick it inside the refrigerator, and I want the heat to go out of that bottle and to be rejected to the room. In the sense that I am trying to go against the direction of spontaneity which was determined by Mother Nature. So the second law says that if I want to do it the other way, it is not impossible to do, right? I can take a cold body and I can make it cooler. I can remove heat even from the cold body if I want. But in order to do that, I will have to pay a price. That is what the second law says. And what is the price that we pay for that? Electrical work. So I take this room, I can make it cooler. I can take that bottle of water that I put into the refrigerator and I can certainly remove heat out of it. But in order to do that, I have to pay the price of electrical work. I have to connect it to the power grid, and I have to do electrical work in order to go against the will of nature. So provided these two laws are satisfied, heat will flow from one body to the other. Yeah? Any questions so far? It turns out that there are three mechanisms of heat transfer. Three modes of heat transfer. The first mode of heat transfer is that if I have a body, a solid body, and if I expose it to hot surroundings on one side and cold surroundings on the other side, then heat transfer will happen from the hot side to the cold side. Right? And this is something that we experience all the time. I take a cup of coffee, I take a spoon and I dip the spoon into the coffee. What happens to the temperature in the spoon? It slowly becomes hotter and hotter, right? How many of you cook? Right? You've experienced this. You're cooking something, you're cooking something, you take the spoon, and if you leave it there, you go do something else, and then you want to stir it, you come back and you touch it, and it's gotten very hot, right? And it almost burns you if you are not careful, right? That is this process in which heat flows from the hot side to the cold side of a solid body. Here is this liquid, here is my spoon. one side is hot, the other side is cold, heat transfer will happen from the hot side to the cold side. Okay? Now, not all spoons are the same. If I do this with a steel spoon versus a wooden spoon, you will realize that the hotness experienced on the other side is very different. Right? A wooden spoon will not conduct a lot of heat. This process is called thermal conduction. And it turns out that the amount of heat that flows depends on the material. If I take a steel spoon versus a wooden spoon, the amount of heat that will flow across the two will be very different from each other. Mathematically speaking, the amount of heat transfer that occurs is given by a very simple equation. Q double prime equals negative K dt dx. So if this is the x direction, then this equation, which is called Fourier's law, basically predicts that the amount of heat that will flow due to thermal conduction is proportional to the temperature difference, the temperature gradient in that solid body. It does. The cross-sectional area comes into picture because Q double prime is written in terms of heat flux, watt per meter square. Okay, so what is Q double prime x? Q double prime x is the amount of energy that passes in the x direction per second per unit area, joules per second per meter square, which translates to watt per meter square. Yeah? On the right hand side, I have negative K dt dx. dt dx is the temperature gradient across this body. How many Kelvin per meter? If the temperature difference between the two is larger, there will be more flow of heat. Yeah? If I take this spoon and if I stick it into lukewarm soup versus very hot soup, clearly the second case there will be more heat transfer and the spoon will get much hotter compared to a lukewarm soup. So clearly this is consistent with our own personal experience, right? This equation is it passes our common sense test. Finally, the negative sign exists because the flow of heat in the spontaneous manner will always be opposite to the temperature gradient. If the temperature gradient is negative, as it is in this case, then heat will flow from in the positive x direction. Do you see what I'm saying? If it was cold on this side and hot on the other side, then the flow of heat would be negative. The flow of heat will be in the negative x direction. That is the reason why we have a minus sign here. And K is the constant of proportionality, which is often called the thermal conductivity. It is a characteristic of the material of the body. Different materials have different values of the thermal conductivity. A steel spoon typically has a high thermal conductivity. A wooden spoon typically does not have high thermal conductivity. That is the reason why the wooden spoon does not get very hot. The steel spoon does get quite a lot hot. Okay? I want to make a few more comments here. The first comment is that this thermal conductivity is in general a function of direction. Imagine a three-dimensional Cartesian world. The thermal conductivity in the three directions x, y and z could be different from each other. In most materials that does not happen. If I take a block of copper, then the thermal conductivity of this block of copper in the x, y and z directions is expected to be the same, right? However, if I take a composite material such as carbon fiber composites, in which I have fibers of carbon embedded inside a plastic matrix, and these kinds of composites are used very commonly these days, right? What is the most common example where we use composite materials? Sorry? Buildings, yes, absolutely. Sorry? Automobiles, aircraft. Traditionally, aircraft was typically made up of aluminum, but now most aircrafts are made up of carbon fibers. Exactly, carbon composites. So in carbon composites, what we have is that you have carbon fibers embedded inside a matrix of some other plastic or polymer, and in this case, you can clearly expect that heat transfer in the three directions will be different from each other. Along the direction of the carbon fiber, heat will be able to flow very easily, whereas in the other two directions it may not be able to flow that easily. And so in this case, heat transfer will be anisotropic or orthotropic, whereas this, the heat transfer is mostly isotropic. The word isotropic means independent of direction. It will happen the same in all three directions. It turns out that heat transfer in lithium ion batteries is highly anisotropic, and we will talk about that in the coming lectures, the reasons behind it and what it means and so on and so forth. By the way, what are the units of thermal conductivity? You can see exactly from this simple equation you can say that this must be watt per meter Kelvin. What are typical numbers for thermal conductivity? For copper, absolutely around 400 watt per meter Kelvin. For wood, I don't want to take the example of wood.
So we used to study for the least method, it's coming around 0.02.
Yes, absolutely. For plastics, for wood, mica sheet, those kinds of materials, the thermal conductivity is much lower. It's of the order of 0.1 to 1 watt per meter Kelvin, very low. Sorry, this thing sometimes does not, yeah, 0.1 to 1 watt per meter Kelvin. These are typically good conductors of heat and these are typically poor conductors of heat. And in the coming lectures, we will see where lithium ion cells fall in this regime. Any questions so far? Finally, I also want to say that thermal conductivity itself could be a function of temperature. As the temperature changes, it is possible that the thermal conductivity of the body also changes. Typically, oftentimes, we neglect that temperature dependence. We assume the thermal conductivity to be a constant number, but that may or may not be the case always. Okay? What else do I want to say here? I think that is all. So the second mechanism of heat transfer is called convective heat transfer. And convective heat transfer is the heat transfer that occurs due to relative motion between a fluid and a solid. So you need to have a fluid and a solid. When I say a fluid, the word fluid could refer to either a gas or a liquid. So if I have a solid body, such as a plate, and if I blow air over this plate, then if the plate is hot and the air is cold, then as the air passes over the plate, it steals a little bit of heat from it. It scoops a little bit of heat and takes it away with it. Because of which this air will get hotter and this plate will get colder. Okay? It can certainly happen the other way also. If this plate was cold and if this air was hot, then due to convective heat transfer, some of the heat will flow from the air into the plate. Yeah? Can somebody give me one example of each case where I have a hot solid body and some cold air blows over it? Where does that happen?
Extraction process.
Sure? Cooling of a transformer, absolutely, or any electronic device. There are so many electronic devices, a computer chip, a semiconductor device, etc., MOSFETs and all that, that get very hot. I blow air over it, because of which the solid body cools down. Right? Any examples of the opposite where I have hot air blowing over something cold, causing it to heat up? Welding? No, not quite. External unit of an air conditioner, yes, absolutely. In the external unit of the air conditioner, I have, or the internal unit is it? Internal unit, where I have basically a series of tubes that carry some cold fluid, right, over which I blow hot air or room temperature air. Because of this process, the air gets cold, and that is the air that comes out of the ducts and cools down our air conditioned room. Right? This process in which this hot air is able to transfer some of its heat to the pipe and become cold is also convective heat transfer. Finally, I want to bring your attention to the word relative motion, which means that either the air or the solid plate could be moving. In this case, I have the solid plate is stationary and the air is moving. But there are also engineering examples where the opposite happens. Can somebody think of an example?
The lathe operation.
Yes.
They used to have the lubricants over there.
Yes.
Both will be having a relative.
Yes, absolutely, absolutely.
Cooling of IC in the pipe. Generally, in stationary air.
Yes, absolutely, absolutely. The air there is stationary and the car is the one that is moving. An aircraft is another example. When an aircraft flies, the air is sort of stationary and it is the aircraft that is moving through the stationary air. And even in that case, there is heat transfer that occurs between the two. Right? There needs to be motion and there needs to be a fluid and a solid body. That is when convective heat transfer occurs. Just like in the previous slide, I had given an equation, a very simple equation for conduction heat transfer. Similarly, the equation for convective heat transfer is also very simple. On the face of it, it is Q double prime equals H delta T. Actually, an extremely simple equation. What it says is that the amount of heat transfer that will occur between the plate and the air, this is Q double prime, per unit area is given by the temperature difference between the two multiplied by this coefficient called H. This very simple equation is called Newton's law. So Isaac Newton in addition to discovering gravity, also discovered this very fundamental law of convective heat transfer. So you can say safely that convective heat transfer is studied only by the most brilliant students. Okay, we are all following in the footsteps of Isaac Newton here. H is called the convective heat transfer coefficient. As you can guess, H has units of watt per meter square Kelvin. Okay. What is the meaning of H? H basically captures the fluid mechanics of the relative motion. In other words, H governs how well the flow and the plate are interacting with each other. Imagine if I have two cases, I have the same plate in both cases. In one case, I have air coming in at 1 meters per second. In the other case, I have air coming in at 100 meters per second, let's say. In which case do you expect more heat transfer to occur? The first or the second case? Okay, let me give you another example. You have a cup of tea and you want to cool it down because you want to drink it. What do you do to cool it down? You blow on it, right? The harder you blow on it versus the faster it will cool down, right? The relative motion, the extent of motion, the velocity of motion plays a very big role in determining the amount of heat transfer that occurs. And that is captured by H. The heat transfer coefficient H is a function of the velocity, the properties of the fluid, and the geometry. Velocity you already saw, right? The nature of this fluid also makes a difference. Whether you blow air over this solid or you blow water over this solid also makes a difference in how fast this solid is going to cool down. Because of its properties, water will be able to remove a lot more heat compared to just plain air. And finally, the geometry of this plate also makes a big difference. Imagine if I have two plates. I have one plate that looks like this. It's a smooth plate. Versus, I have a plate whose surface is rough. If they're at the same temperature, if I blow the same amount of air across both of them, in which case do you expect more heat transfer to occur? Not smooth. The rough one, yes. Why? Yes, because it is able to come into touch with it more intimately, this air that blows over it. Right? Whereas the smooth plate, the air just glides, just passes over it, does not have an opportunity to really get to know the plate. Right? So if the plate is rough, in other words, the geometry of the plate also makes a difference in the extent of convective heat transfer that occurs between the two. So there are a bunch of convective heat transfer correlations. That are equations which create a connection between H as a function of the velocity, the properties, nu, alpha, etc., and the geometry as well. So yes, sorry. Uh, Good question. If the change in pressure causes a change in velocity, then yes. But if the velocity remains the same and you change the pressure, then that by itself will not change anything. Okay? The pressure can also change the properties of the fluid. So it can have multiple effects on each of these things that ultimately affects the heat transfer coefficient.
But Boyle's law cannot directly do.
Boyle's law can predict that. Boyle's law, PV equals nRT, exactly, yes. So, yes,
Does the property of plate also affect?
that's a good question. The properties of the plate do not affect the convective heat transfer between the two. The game of convective heat transfer is played entirely on the basis of the properties on the air side. Whether this plate is made up of wood or it is made up of copper, as long as its temperature is the same, it does not affect the rate of heat transfer. Okay, that's a very good question. So in the world of convective heat transfer, over the years, different people, through either measurements or theoretical analysis, have proposed a bunch of these different correlations that are available to you for use. So if you have a plate of a certain size and if you have air blowing over it, you can look up these correlations to be able to determine the value of H. And once you know the value of H, you can very easily, through this equation, determine how much heat transfer occurs between the two. So in the world of convective heat transfer, step number 1 is to find out the value of H for your specific geometry. So for example, if your solid body is a cylinder and if you have air blowing over it, so that the air will blow over the cylinder in a manner like this, then there are very well known equations that tell you the value of the convective heat transfer coefficient in terms of the diameter of this cylinder, in terms of the velocity of the air, in terms of the properties of the air, and so on and so forth. In this world, in fact, we commonly use non-dimensional numbers. And those of you who have taken a class in heat transfer or fluid mechanics will know that one of the most common non-dimensional number here is the Reynolds number, which is given by ud over nu. U is the velocity, d is the diameter of the cylinder, and nu is the viscosity of the air that blows over it. And the convective heat transfer coefficient is typically represented by the Nusselt number, which is given by hd over k. And typically these correlations are written in terms of Nusselt number is a function of the Reynolds number and also the Prandtl number. Okay, this is the Reynolds number. Please don't make spelling mistakes in the names of people. Okay, it is the nu is given by mu over alpha, mu over rho. I forget which one is called kinematic, which one is called dynamic. I think this is the dynamic viscosity. Kinematic, okay, thank you. So this is the kinematic and that is the dynamic. Okay. I was saying, please don't make mistakes in the spellings of people. Right? My name is Ankur Jain and I want it to be Jain. That is how my parents gave me my name. Right? If somebody calls me, makes a mistake in my name, I will not feel good about it, even when I am dead. Right? So all these people are long gone. But I feel that if you make a spelling mistake in their names, wherever they are in their graves, they will curse you from there. Okay? So please don't do that. especially with Reynolds. His name was Reynolds with a S. There is no apostrophe here. Do you see what I'm saying? This is not the number of Reynolds. This is simply Reynolds number, right? So please never use this apostrophe with Reynolds. Okay? Promise? All right. So for example, this non-dimensional correlation, for example, often we write Nusselt number equals C times Reynolds number to the power n times the Prandtl number to the power m, where you can go to well-known textbooks and find out the values of C, n and m. For example, for flow over a cylinder, I think n is of the order of half and m is of the order of 1/3, etc. It all depends on the geometry. Instead of the cylinder, if you have a sphere or if you have a rectangular cross-section body, then this equation might change. You know what I'm saying? But at any rate, you don't have to do the hard work for deriving these equations. These equations are already available to us in a good resource. For example, the most common resource for heat transfer, introductory heat transfer, is this book by Incropera. And do it. When Dr. Tyagi and I were students 25 plus years ago, we had used Incropera and Devitt for learning heat transfer. 25 years later, when we are now teaching the next generation, we still use Incropera and Devitt, right? So this is a very standard, sort of like the Bible of this field. Now there are other authors as well, but if you just search for this, you will find out what I'm talking about. It's an excellent book. Okay. So I just want to connect what we are talking about with lithium-ion batteries. If I have a cylindrical lithium-ion battery, which is indeed the case for most electric cars and electric scooters, the battery pack, it has a bunch of these cylindrical lithium-ion batteries. Not just one, but hundreds, sometimes thousands of these single cells that are arranged sort of in a fashion like this. I'm drawing the cross section here. These cylindrical cells will generate heat, and if we don't remove the heat out of these cells, they will overheat and cause all kinds of problems that we will look at in subsequent lectures. How do I cool these down? The simplest way is to blow air over these bank of cylinders. And if you are working for a startup company that is trying to create an electric scooter or something like that, this will be the key question to you. If I have a fan blowing air over this bank of cylindrical lithium-ion cells, how much heat will you be able to remove? How hot will these cells get? And whether the battery pack will be safe or not. In order to solve that problem, we start really from this very fundamental equation, Q equals H delta T. We find the value of H from correlations like this, right? And that tells us how much heat I can remove from a cylindrical lithium-ion battery. Okay. Surface area also plays a role, and the surface area appears here in Q double prime. Q double prime is watt per meter square. So if the surface area is larger, I will be able to remove more heat. So, just to connect this with cells, if I have if I am designing the cells themselves, if I work for a company like Panasonic that is going to build these cells, and somebody comes to you and says, I have a given volume of the cell, I can either create a long and thin cell, or I can create a short and large cell. The volume is the same in both of them, but the surface area is different. Correct? And the amount of surface area available for heat transfer makes a very big difference, as you can see in this equation. This equation says that the larger the surface area, the greater will be the heat transfer that will occur, right? And therefore, as a battery manufacturer, from a heat transfer point of view, you want to maximize the surface area available for heat transfer. If you blow, the direction in which you blow air also makes a difference. If you blow air like this versus into the plane of the paper, the amount of surface area available is different, right? Or versus at a certain angle or whatever. So you can see that these very fundamental principles of heat transfer can be used to create a first level thermal design of the battery pack. Typically, we spend an entire semester teaching heat transfer principles, right? I am going over it from a very broad overview, condensing the contents of one semester into just one lecture. But you can certainly look at other resources such as Ropar and Devitt for more details of heat transfer. In our short course, we will certainly use a lot of principles of heat transfer, both conduction and convective heat transfer. Another example that I will give to connect this discussion with batteries is the following. The battery pack that I drew here is basically an open battery pack, meaning that I have a bunch of cells and there is air between the cells, and therefore I can blow air over the battery pack. Oftentimes what happens is that I have a solid block in which I will insert multiple lithium ion cells. I don't know if this is clear. Sorry, let me just draw this again. I don't think I did a good job here. What I'm trying to say is that we have a solid metal block in this solid metal block. I will drill holes and make space to insert lithium ion cells. In that case, if I blow air over this body, then the air will not directly touch the cells. The heat generated inside the cells has to first conduct through the solid body to the outside surface of the solid body, and then the air blowing over the outside surface will remove heat. So it's a two-step process. In step number one, heat has to flow from the cylinder through the material of the solid block, and it has to reach the outside surface, and then the air blowing over the outside surface will remove heat. So step number one is conduction. Remember, conduction was the flow of heat through a solid body, right? And then the second step is convection, which is due to relative motion between the solid body and the flow of air. So we need to understand both conduction and convection in order to understand the nature of heat transfer that will occur in this battery pack. Okay, let me actually show you, if I can find here. Oh, sorry. wants to sell it to me is the problem. For example, this. So what is happening here is that I have multiple individual cells that are connected to each other and put together as a pack. If I blow air over this, there is only air between these cells. And so the nature of heat transfer will be mostly convective heat transfer. But if these cells were placed inside a metal block with holes in the block, then both conduction and convection will become important. Okay? The third mode of heat transfer is radiative heat transfer. It is probably the most neglected of the three for two reasons. One is it is not as common a factor in most engineering problems, and secondly it is mathematically more difficult to understand and analyze compared to radiation, compared to conduction and convective heat transfer. For those reasons, radiative heat transfer is probably the least studied of the three. It's a little sad in some sense, but that is what it is. For a lot of applications of lithium ion batteries, radiative heat transfer is not the dominant process. Conduction and convection are much more vigorous and strong compared to radiative heat transfer, and for that reason we will not discuss this too much in our class. For the purposes of thermal management or heat transfer in a battery, conduction and convection are the most important processes. Just to repeat, conduction is the flow of heat within a solid body because of a temperature difference, governed by a very simple Fourier's law in which the thermal conductivity appears, and convective heat transfer is the flow of heat because of relative motion between a fluid and a solid body, which is also governed by a very simple law, except that the convective heat transfer coefficient H, it's not a property of anything, right? Earlier we said that thermal conductivity is 400 for copper, 0.1 to 1 watt per meter Kelvin for plastics. That is not as simple for H. For H we need to write these correlations, and these correlations are what will give us the value of H. Typically we use non-dimensional numbers, and the convective heat transfer coefficient is represented by the Nusselt number. The Nusselt number usually a function of the Reynolds number and the Prandtl number, right? So we are done with time, so I'll stop here. All I will say to finish up is that these fundamental concepts of heat transfer we will begin to apply in understanding the nature of heat transfer in lithium ion batteries as we go forward. So the agenda for the rest of the day is that after lunch we will have a 1.5 hour lecture on the electrochemistry of lithium ion cells, which will be taught by a local faculty at IIT Ropar, and then I will come in later in the day to teach a tutorial in which we will take these principles of heat transfer and we will put some numbers, and I will solve a few representative problems in order to determine the nature of heat transfer in a very simple battery system. Alright, so are we good to stop at this point? Let's do that. It's past 12:30. What time do you want everyone to be here? Okay, so we will start the next lecture promptly at 2 o'clock. So please go have a good break. I will be around if you have any questions to ask me, and we will see you all back at 2 o'clock. Alright, thank you so much.
Hello, is it fine? Okay. Okay, fine. Yes. So welcome everybody. Those who are not from IIT Ropar, I think there are a couple of students from IIT Ropar. They already know me. But for others, myself Manish Agrawal. I'm a faculty here in the mechanical department. Okay. So we will talk about. So Ankurji here is mainly taking care of the thermal aspect of the electrochemical battery molding and its ramification, that how the temperature changes and these things actually do affect in the practical scenarios, right? Here we are not going to go into the thermal aspect. This is mainly is going to be the electrochemical aspect of the battery modeling. Okay, so this is at least, so the overall content is going to be slightly on a mathematical heavy side. So those who are not that much comfortable, please stop me whenever you want, and we can see like how I can make the I will change the communication accordingly. Okay, so feel free to stop me anywhere. There is no issue whatsoever. Okay, and yeah, so I actually work on the mainly on two aspects. One on the FEM development, finite element algorithm for various systems. It may be battery, it may be a normal mechanical system, or we work on the deep learning aspect of the various physical system, right? How do we actually can come up with the deep learning algorithm for those? Anyway, but today's topic is a bit different, so let's start. Okay, with this. Okay, so as I told that we are going to talk about electrochemical modeling of battery system, right? And most of the content that I am going to present for the next two lecture is actually taken from this particular paper. Okay, it's a very nicely written paper, very comprehensive, uh, written, and quite systematically done the job. And the reason that actually rather than citing it in a conventional way, I put the snapshot is because I wanted to highlight one thing, and that is the author affiliation of this particular paper. Okay, so if you see, some of them are from chemical engineering, some of them are from the civil engineering, some of them are from mechanical engineering, and even I think one was from mathematics also. Mathematics also, right? Electrical, right? So you can see the, so this I put it just to highlight the multidisciplinary nature of the battery research, that actually irrespective to your stream you can contribute into this particular field. And this paper was possible because there were so many different stream people actually collaborated. Okay, so that's the reason, and most of the content on my slide is actually borrowed from this particular paper. Fine. So before we actually go, so as it is written in the title, we want to discuss the lithium ion battery models, right? So why we want to model, first of all? Why we want to actually design a computational model? What is the need of the computational model? Okay. So why? Sorry. Yeah, you can actually keep on asking or interacting. Why we want to model the lithium ion batteries? So any comment or any input from the audience? Huh? No, I couldn't get. For optimization of what? No, no, but that is fine. That is always the goal of any simulation. It's ready to minimize the experiment. But that is a very generic statement, right? First, the question is why, like, what are the answer we are looking from the electrochemical battery simulation?
To understand the quantitative perspective of it.
Okay, so you understand the quantitative aspect, right? Which is physically quantitative aspect?
Where we have a list of battery related parameters.
Yes.
Electron density,
Uh,
charge density, charge carrier, charge
uh,
mobility, and other kind of things.
So these are actually, in case of lithium ion batteries, these are actually physics based detailed model. So we are actually going to understand how the things are actually happening in the positive electrode, negative electrode, what is happening in the electrolyte. Right? So what are the output we are looking for?
Enhance the efficiency.
That is again a bit generic. We ultimately want any system, we want the efficiency to be enhanced, but in specific, what are the output we are looking for? Huh? Amount of the energy stored. Okay, so fine. So amount of the energy or amount of the energy I can draw in a particular cycle. Okay, that can be one of the output. Okay, in particular, let me do it. So ultimately, one of the plot that I am looking for is the voltage that is going to be produced from the battery and the time or in some way uh, state of charge. Okay. So how the voltage response of the battery? So what is the typical voltage of the lithium ion battery? Anybody know? You want to reduce the pen? You can close if it is creating. Acha, it is not, sound is not audible. We can reduce this. Is it fine now? So what is the typical voltage of lithium ion battery? Okay, 4.2, 3.6. Okay, these are the typical number. So, but that is actually when the battery is fully charged. Okay, but as the battery, when the battery is 100% charged, then the typical voltage is 4.2% voltage. But slowly, actually, the terminal voltage actually decays, right? So the typical graph looks like this. Okay, but this is actually not. So this particular response depend on how much fast you are doing the charging, or actually in this particular case discharging. Okay, so it depend on that. It is not something which is like a fundamental characteristic of the battery that is given to you and that is going to be work for every kind of load cycle. So for example, you see in nowadays there is a lot of emphasis on the battery development, like how fast you can charge your battery, right? You want to charge in 1C, 2C, right? So you want to charge your battery as fast as possible, right? But why not everybody actually just start charging the battery? Like just supply more current, it will charge faster. But there are ramifications to that. Okay, so this actual capacity, one is the theoretical capacity, one is the actual capacity that you actually get out of the battery in a particular condition, right? So that depend on the charging or discharging speed, right? So we want to know that till what charging or discharging rate we can actually draw a sufficient amount of the power, right? Second, uh, for Ankorji to do calculation on the thermal aspect, he will need certain parameter from the electrochemical physical model. For example, the voltage, current, whatever those macro level parameter, right? So those also we want to give it to the thermal model, right? So this is one more aspect. Another aspect, somebody told optimization, right? So ultimately I want to design what is the separator length, what is the porosity of the separator, what should be the, again I will explain those things in a more detail, what should be the cathode particle radius or positive electrode radius. So I want to determine all these parameters and I want to see that how these parameters actually affect my overall battery performance, right? That is one more thing. And lastly, I want to see even how fast my battery is going to degrade. Okay, whether it is going to last 1 cycle, 10 cycle, 20 cycle. Although we will not go too much into the detail of the degradation model in this limited time, but those you can actually model the degradation mechanism along with the electrochemical model that we are actually discussing. So all these things you can do with this physics based model. Okay, so we'll discuss today all this aspect of it. Before we jump into the this electrochemical battery aspect and other things, let's first revise one of the key mathematical concepts that we are going to multiple time we are going to refer. Okay, and that is known as Gauss divergence theorem. Okay, so let's just to make sure that everybody is understand that. Okay, so let's say there is a one particular arbitrary domain is there which has a volume V here. Okay, and or let's call it, let me call it omega to be consistent with the rest of the lecture, and the boundary of this or the area of this I called as a del omega. Okay, these are the typical notation I am going to use. Omega to refer to any domain, capital omega, and partial of the omega to denote the boundary of the domain. Okay, so you can imagine, for example, this is the bottle, sorry, and the boundary of this, whichever is on the surface, is the partial omega, and overall domain that is there is the omega. Right? Now, the Gauss divergence theorem tells that suppose there is a vector, arbitrary vector v, okay, and I draw a normal n tilde. So n tilde is a unit vector which is normal to the domain boundary. Then v tilde dot n, if I carry out the integration over the boundary, that is equal to the divergence of v over the omega. Okay, just for other understanding, the divergence of the v is defined as del v1 over del x plus del v2 over del y plus del v3 over del z, where the v tilde is vx, v1, sorry, v2 and v3. Okay, so v tilde is an arbitrary vector which has three components, v1, v2 and v3, and the divergence of that particular vector is defined as del v1 over del x plus del v2 over del y plus del v3 over del z, right? So this Gauss divergence theorem, which is written here, what it does something very extraordinary actually. So if you see this integration, this is carried out on the surface, that means here on the surface, right, and this is carried out at the volume, means inside the domain. Now whenever you are carrying out the integration, right, you are actually summing up the things. Integration is like a summation. So when you are carrying out this integration over the inside the domain, it is in the volume, right? So you need the information of del dot v or the v inside the domain, but it is able to convert this del dot v which is inside the domain into the boundary. So here you need only the information at the boundary. Okay, so something for which you need the information everywhere in the domain, you are able to convert to something which you only require at the surface, right? So that's why it is an extraordinary theorem, and it is actually used a lot irrespective to the engineering thing. Okay, so we will not be needing too much detail, but we will just needing the statement of this particular theorem, that is v dot n ds equal to divergence of v over the volume, right? Fine. Now we'll come back to our battery thing. So in battery, if I talk about, so as you can see the slide, there is a word that is mentioned, physics based model. So in today's lecture we are going to talk about physics based model. There are other model, for example, those are known as equivalent circuit models, which are more empirical models. So here we are not going to talk about right now those. There are some data science based model also. Again, we are not going to talk about those. We are going to talk about only physics based model. So the most refined version of the physics based model is known as micro scale model. That is the most detailed one, where you are putting almost everything that is there in the battery in the your model. Okay, that is the most uh, detailed kind of calculation that you can do. There is a slightly coarser level of the model that is known as homogenized model. That is the second level of the model. Okay, and so there is a simplification from the micro scale to the homogenized. Again, I will go into the detail as we go along. Right now, just giving the overall picture. Then there is a model called as DFN model, or more popularly known as P2D model. This is perhaps the most popular model that is there for battery model. Whenever you do the electrochemical analysis in software like COMSOL, by default you are using P2D or DFN model. Okay, so this is a kind of 1D model. Actually, it's known as pseudo 2D model. Why it is known? Then again, I will explain to you later. Then there is a more simplification version of that SPME, where uh, electrodes are modeled as single particle, and then the most simplified form is the SPM. Okay, so we will try to start the lecture with the micro scale version, which has all the details. Then we'll move on to the homogenized model. After that, we will see how you can actually drive the, not actually drive, but at least get some overall steps. How do you go from micro scale to homogenized model, and then homogenized model to how you actually go to the DFN model. Okay, that is the overall idea that we want to cover. After that, this you can do the reading on your own, that how to make the more simplification assumption. So we'll try to cover the first three, that is the goal. Okay, in the next two lectures. Fine. So let's see the schematic first. Let's try to see that what are the things we are going to talk about, right? So this is the overall layout, right? So first I will also try to draw here, and the reason is I would like to at least have some drawing with me when I talk about the equation, and here I am going to write the equation, so let me do that. Okay, so the first thing, let's start from the rightmost. Okay, rightmost and leftmost, right? There are two blocks. These are known as current collector. Okay, so they are just metal strip which are just taking out the current from the lithium ion battery to the external circuit, nothing much. So these are not something fancy, these are quite preliminary stuff, right? Now after that we have positive electrode, right? So this is the positive electrode. I will just denote it with the symbol P. Okay, then there is a separator. Okay, and then there is a negative electrode, which I am going to denote by letter N. Okay, and separator anyway we won't need the symbol, but let's completeness, let's write the S, right? So let's try to see what it is contained, right? So if you see this positive electrode, it is not there is some kind of these particles, right? So I think Ankurji was talking about some kind of lithium compound which makes the positive electrode, if I am correct, some kind of lithium cobalt oxide, right? So these green particles are those only, or any sub alternate to that. For example, I think there is a magnesium MnC. Yeah, it is called as MnC. So there, so it can be actually particle of those. Okay, sorry. Right. So ultimately, whatever the underlying material is there, these are the particles. Okay. Now you see bunch of black particles flowing here and there. These are binders to keep all these particles, the actual particle where the lithium is there, to hold them together. So these are the binders who are not actively participating in the chemistry of the battery. They are just there to act as a glue. Okay, their role is there. The blue thing that I am showing actually is the electrolyte. Okay, so unlike the conventional picture that you have, that the electrolyte is different, electrode is different, this is not how the lithium ion battery is. Okay, inside the electrode also there is an electrolyte, and actually it is a very important thing to know when you are doing the modeling. So electrolyte is present in the electrode also. Electrode is a porous medium where the electrolyte and the electrode particles are actually present in the same domain, right? And there is another name for that, and these particles are also known as, commonly referred as, active particle, because they are actually actively participating in the overall domain, right? So these are known as active particle. So this is about the this one. The domain we are going to refer this as a, as I said, we are going to use the symbol omega, and we are going to use subscript omega p to denote the domain occupied by the positive electrode. Fine. Now let's move to the left. So now we have a separator. Again, separator is a porous medium. Here the separator is there and the electrolyte is also present. Okay. Separator job is not to allow the electron, it doesn't allow the electron to move, it allows the ions to move freely, and it doesn't allow the electrons to go from the, otherwise there will be a short circuit, right, between the, in the battery. Now if I go further there on the negative electrode, then I have graphite, right. The negative electrode is typically made of the graphite, C6 sorry, and again there are some binder, other kind of things to keep it together or other things, and again this is also a porous domain, so here also electrolyte is present. Okay, and then we have the current collector, right. So the summarizing overall thing, everything is a porous, everywhere the electrolyte is present. Okay, whether it is in the electrode region or it is in the separator region, everywhere there is electrolyte, and you have the active particle and you have the graphite here, right. So what are the reactions that are happening? So in case of discharging, so in case of, let's say the battery is fully charged, what will happen that time? Where is the lithium? So if the battery is fully charged, all the lithium is here, right. Now you are discharging the battery, right. So what is happening? Lithium here is actually getting broken into the Li plus and electron, right. The lithium is, positive ions are actually moving toward the positive electrode, right, and the electron are actually going away in the external circuit, and then the electron takes the whole path, come back here, and then Li plus electron again make the lithium, right. Okay, fine. So in electrode, if I see, there are two things that are moving. What are the two things that are moving? One is lithium, not lithium ion, okay, lithium and electrons. Okay, lithium ion is not moving, right. Lithium ion is, huh?
Electrons in lithium ions.
No, lithium and electrons are moving. Lithium ions are moving inside the electrolyte. Okay, these are the two things which are moving in the electrode. Okay, and what is moving in the lithium ion is moving in the electrolyte. We should know that which species is present in which domain, then only we can actually do the we can develop the model. So lithium ions are moving in the electrolyte. Apart from the lithium ion, which are known as cation, because these are positive ion, they are negative ions also moving. Okay, for example, if you have Li PF 6, then it is Li, I think LiPF, right? Li plus PF negative. Sorry, I don't remember the exact formula. LiPF 6, and here also it will be PF6, right? Thanks. Right. So there is a cat. So in electrode we have lithium and electron. In electrolyte we have the lithium ion, and I am writing X minus some kind of anion. Okay. So this is in the electrolyte. Fine. So let's go to now again. Sorry. Acha, new one means this is what. Fine, thanks. Okay. Fine. So now let's talk about the electrode, right? And then we'll go to the one, right? So in electrode, first talk about. So let's talk about the conservation law in electrodes. Okay, sorry. Let me know because sometimes this pen is not writing it. Okay. So first talk about there are two species. One we are going. So let me define something. You know what is Faraday constant? Or you know first what is mole? What is 1 mole? There is a number, right? 6.023 into 10 to the power 23. Right? So 1 mole means this is number of atoms of that or molecules of that particular quantity, whatever is the quantity. So this is rather than being this is just the actual number, not the mass or something. Okay. And the Faraday constant means the charge that the electron is 1 mole of the electron carries. Okay, that is the Faraday constant, amount of the charge that is present in the 1 mole of the electron. Okay. So conservation law in electrodes. Fine. So let's talk about the 1 second. Lithium. Fine. So now let's see. I have drawn, right. There are a bunch of active particle, right. Okay. Now in this bunch of active particle, I am taking a small domain here. Okay. So the domain is even smaller than the any of the particle. Right? And now if I take this domain and again draw it. Okay. Let me draw it in a more complicated way so that you don't confuse with the active particle. Okay. So then there are two things that are happening. One, the lithium ions are actually moving out, right. I am just by convention I am taking the moving out thing. If I take the negative of that, that is a moving in thing, right. So the moving out, I am going to denote the flux as N tilde lithium. That is the flux. And you understand the flux, right? For example, if there is a pipe flow that is happening, right? And then what will be the flux? That will be the velocity into the area, the amount of the flow that is actually happening, right? So this is the flux that is happening, and the concentration of the lithium ion I am going to denote by CLI. It's not. to write it very slowly. So this CLI is the concentration of the lithium. Okay, the unit of that is mole per unit volume. Okay, so the unit is of the concentration is mole meter minus cube, right, per unit volume, right. So now let's do the mass conservation. Okay, so the amount of the lithium that is there inside the volume is the concentration CLI integration of this okay, or you can note it right, dV. Okay, this is the total amount of the lithium that is present in this volume. Okay, and what I am doing, I am writing the derivative with respect to the time. Okay, how much it is changing. So rate of change of the lithium mass, that should be equal to the amount of the lithium that is going away. Sorry, actually it should be the negative of the amount of the lithium that is going away, right. So then it will be minus of n tilde Li dot n. Okay, what is the flux? Right, flux is a vector, and then I am taking dot product with the normal, because whatever is happening in the tangent direction, that is not going to go out, that is just going to be remain within the boundary. So that is the one, and then I integrate it over the whole surface, and that is actually this one. Okay. Now what I do is I apply the Gauss divergence theorem. So then it is going to be del C Li over del T. I take this derivative inside the volume, plus I take this quantity on the left hand side and I apply the Gauss divergence theorem. So this will become divergence of n tilde Li dV, because now I have converted the surface integration into the volume integration. Now if I combine these two terms, then it will become del C Li over del T plus divergence of n Li, that is the flux overall thing, into dV over equal to 0. And because this is an, now I don't want to go to the mathematical argument too much, but just for the completeness, because this is an arbitrary domain, I can actually conclude that the integrand of this is actually equal to 0 when this integration is 0. So then this is going to be del C Li over del T plus del dot n Li equal to 0. Okay. So this is the conservation law for the lithium inside the electrode. Fine. This is actually although we have, out of the 4 things, or actually in total there are 6 things, this is the standard form, and this will be the form that is going to keep on occurring again and again. Okay. So the main thing is to understand this particular relation. Yes. Yeah. Yes. dV is the volume of the arbitrary small, infinitesimally small domain. Okay, domain. ds is the surface. No. So in general the theorem applies for any surface or something, but here the discussion is restricted to the electrode particle. So this is the electrode particle. Inside the electrode particle, I took a very small domain. Okay, so that's why I have drawn here, right? So from here, this is the one. Okay, and then this is the domain I am talking about. So this domain is actually the omega, and the boundary of this is actually the partial or del omega actually. Okay. No. This boundary is arbitrary, but it's not changing. Okay, the boundary it's not a moving particle I am taking, but it's not a deformable domain I am taking. So this boundary is fixed with the time. That's why I can take the derivative inside the domain without any issues. Okay. So just for if you want to connect, you know the heat transfer equation, right? So in the heat transfer also, just to quickly connect with other things, if you have a domain, you have the heat that is going flow out, that is q dot n. Inside the heat that is changing is rho Cp del T over del T, assuming the rho and Cp is constant with respect to the time. That is the heat that is changing in the volume in the domain, right? In the total domain, and that I can actually equate to minus q dot n ds, and I can do the same step, and ultimately I will get rho Cp del T over del T plus del dot q equal to 0, which is actually the heat equation. Okay, so this particular form is very common. It is not if you drive the mass conservation, again you will have the same kind of form. In heat equation also it is the same form. So the steps are actually used in various domain, and the form that you will get at the end is going to be more or less similar. Sometimes there may be vector, sometimes there may be tensor, that is a different thing, but at the end of the day you will get always the same form. Okay, so you can relate with the heat equation also. It is the same thing, right? Rho Cp del T over del T. Here the temperature is there is the concentration, there is the heat flux, here there is a mass flux. Otherwise it is the same thing, right? So it's not something very new. Those who are familiar with the heat transfer, they have been seeing this kind of equation anyway, right? Okay. So now the lithium is done. Now we'll move to the second species, which is electron. Okay. Again, the good thing is I don't again need to drive. Conservation law is same. Only thing is there it was concentration of the lithium. Here the concentration of the electron. Nothing else, right? So now let's talk about the electron conservation. So then it is going to be del C E minus by del T plus divergence of N E minus tilde equal to 0, right? Same thing again. The only difference here is actually this term I can drop off to 0. Okay, and the reason is the movement of the electron is so fast that this phenomena, the time scale of this is in the millisecond or nanosecond. So you don't need to consider the first term. Okay, so this equation becomes even more simpler compared to the previous one, and that is the divergence of N E minus tilde equal to 0. Fine. So if you want to call so this is all in the gamma K domain, where K is either P or N. Okay, so whatever the equation we are driving, those are valid in the electrode region, either positive electrode or the negative electrode. So that's why I am calling that this is for the omega K region, and this is the second conservation law that we have obtained. Okay, now let's talk about the third one. Okay, so in a battery we are not only interested in the chemical stuff. There is something called else is happening, that is the electrical stuff, right? We want to talk about the potential, we want to see what is the voltage difference, how the currents are moving or something, right? So we want to do the conservation of the charge also. Okay, so let's take the, so conservation of the charge may be different from a conservation of a particular species, because huh? Because this okay, so let's say here the this, you know, right, delta or q, right? You know what is q in general? Heat flow. So Fourier law of heat conduction says that q is equal to minus k dt by dx. If the k is very high, how much time it will take for the steady state to reach? Very fast, right? Instant, and it will reach, right? So this is also like this, that the diffusion of the electron is very fast. The diffusion constant of the electron is very, very high. So it will be so fast that you don't need to consider. Okay, so ions are moving at the time scale of second, electrons are moving at the time scale of microsecond and the nanosecond. So you can neglect the time difference. Okay. So it is so fast that for you it is stationary. It's not uniform, it is changing with respect to x. Time derivative is 0, so it is changing very fast. So that's why the time with respect to time it is uniform. It is reaching the steady state very fast. Okay, so del dot n equal to 0. Now charge conservation. So in general the charge conservation is del q over del t, that is the total charge that is changing with respect to time, plus del dot the divergence of the current equal to 0. That is the charge conservation typical equation again. Okay, because the current is like a flux. Okay, and q is like the total amount of charge. What is the charge actually in our case? In our case the total charge is, in case of electrode, there is the only electron which is charge carrying species. There is no lithium ion in the electrode, there is no anion in case of electrode, only electron is there, right? So q is simply F Faraday constant into C into E minus. Okay, so whatever is the concentration of the electron, if I multiply with the Faraday constant, then I will get the total charge, right? So if you see, if del C E by del T is 0, then del Q over del T also will be equal to 0, right? Because both are the same thing, just multiply with the constant. And other than that, even the second equation that you will get is del dot I tilde equal to 0, right? And this is actually same as del dot F CE minus equal to 0 and del dot CE minus equal to 0. So both this one and this one are actually identical. Oh, sorry, I think I did something. No, 1 second. Sorry, this is not. This is the flux, right? Sorry. Okay, fine. So we have derived 3 equation, but we need only 2 equation because one is actually dependent on another. Okay. So I think I may have it in the slide. Okay, so although I will again refer to this one, but in order to summarize, these are the 2 equations that I am talking about. The first 2 equation, we have not talked about the rest of the stuff yet. Okay, this is the final one which we will discuss at the end of the lecture. The goal is to cover the full slide. Till now we have been able to cover the first 2, this one and this one. Okay, so these, so ultimately in the electrode I have to solve only for the conservation of the lithium and the conservation of the charge, and the first equation is the conservation of the lithium and the second equation is the conservation of the charge. Okay, these 2 are the governing equation. Now okay, I should check the time and then I can. Okay, still time. I think we can easily cover. So what was the unknown in the two equation? There was a C E sorry C lithium, that was one of the unknown, right? Another unknown was flux and tilde lithium ion. Another one was current, right? But the uh, two equation cannot be used to find the three variable. So we need the some kind of relationship between these two variables, right? So the now comes the second one, the what are known as constitutive law. So the NLI tilde is equal to minus D tilde. This is C comma X. Okay, I should actually use the K also, but it's okay. And then I have the gradient of C, right? I think that is fine. Okay, so the flux of the lithium particles or lithium molecule is going to be related to the concentration through this manner. You have seen this law, right? There is a name to this, Fick's law, right? So it is saying, you know, if I can write in the 1D form. So in 1D form it is going to be minus D into del C over del X, right? The way the heat transfer happen, right? From a high temperature to a low temperature. Similarly, if you have two species, right, where one place has a higher concentration, another one is lower concentration. If you take a salt in your kitchen, right, and you put somehow you actually manage to have a you take two solution, one which has a high salt concentration, another has a low salt concentration. You pour them, right, and leave it for some time. They actually will become, over a period of time, the salt will diffuse from a high concentration region to a low concentration region, and they will be equilibrium will be reached, right? So like the way in the heat transfer from a high temperature to low temperature, right? So here also the same thing, right? I am just writing in a more generic 3D equation, that the D into this one. D is known as diffusion coefficient. Now the tricky thing about this D is that the D is actually depend on the concentration. Okay, so whatever is the actual concentration of the lithium in the electrode, the D also depend on that. Okay, so there is a I think I was talking there was a podcast by Elon Musk where he was talking about this, and he gave a very nice analogy. So I will repeat that analogy. So it's like so this is what this law is dictating. It is dictating that how the lithium is actually getting inside the anode or in the cathode, right? So when you are doing the charging, so the lithium is coming and it's trying to go in this graphite seat where to actually go and park myself, right? So try to imagine a parking place which is first empty. So then you will easily find a space and you will park your car and you will go, right? But if the parking space is full, right, then it will take a lot of time for you to figure out where to park myself, right? So if the concentration, so that's why the diffusion coefficient is a function of the concentration, and actually it's keep on going down in general as a function of the concentration. And the ramification of that is, if you see your phone, if you notice the charging of your phone, that 80% charging actually happen very fast. The rest 20% charge takes a lot of time to happen, and that is actually physically that is happening because this diffusion coefficient here is actually a function of the concentration. That's why this is happening. If the diffusion coefficient is independent of the concentration, probably you will not see that kind of thing. Okay, So that's why it's very important. Although lot of in the literature, a lot of time we just take it as a constant, but actually in general, especially if you're not worry about the 80 to 100% charging, you just want to see the 0 to 80%, you can take it then constant. Right? So this is the constitutive law for the lithium one. For the electron, the law is again, I think all of you might know, this is conductivity as a function of x, and then this is del phi, where phi is the electric potential. So you know the Ohm's law, right? I equal to so that is also that is the same form. So if you take this on the other side, then okay. So this is a microscopic form of the Ohm's law. Okay, that is more macroscopic law. If you integrate in everything, then you will get it. So this is the point-wise law that you can apply in the domain. So this is known as also Ohm's law. Okay, so this is sigma. So this is conductivity. Fine, this is current, and if you want, you can put it IK. This is not. If you want to denote that where this current is there. What are you saying? No, need not to be. Current is a vector quantity in this case. Right now it can be drawing in any direction. It is a vector.
Among the partitions, it can be on linear axis. Among the three coordinates.
It can be in any. Right now. Later we'll make, in actual battery it is actually more or less one directional, but that will go later. But right now we are assuming for the model it is an arbitrary vector. Not a unit. Okay. So I am keeping the subscript k here so that to indicate that we are still talking about both of the electrode. K can be p or n. Okay. So this actually complete the picture for the electrode. Now we have to go to the electrolyte. Okay. Electrolyte, the story is unfortunately slightly more complicated compared to electrode. Okay. So in electrolyte now, but the thing is we have done some groundwork, so now we can move faster, although the things are more complicated. So now we have in case of electrolyte we have Li plus, anion, okay, and we have the charge. So again three common equation. Let's write down all the three, and it should be fine, right? So in Ni plus is also same, del C Li plus. The only thing is now I am writing plus because now the conservation of the lithium plus ion plus del dot flux Li plus equal to 0. Same form, right? Just the SPC is changing. Similarly, del C x minus over del T plus del dot and tilde x minus equal to 0. Same again, similar form. I will write here the last one, that is the conservation of the current. Okay, here the current here is Faraday constant into n of Li plus minus of n tilde of xi. Okay, so the current in the electrolyte is not happening because of the movement of the electron, it is happening because of the movement of the ions. Okay, fine, and they are current due to the movement of the positive ion, and there is a current due to the movement of the negative ions, and definitely the charge, the direction of the current is going to be negative of each other. So that's why there is a F n Li plus minus n xi minus, right? Okay, so this is the current, right? So now if you see again, if I know this, I can, if I know 1 and 2, I can get 3, right? Because see, if I know the current and the flux of the positive ion, I can calculate the flux of the negative ion simply. So there is no point again to solve the 3 equation. I can only solve the 2 equation and I will be done, right? No, no, no. It is right now we have not gone to the homogeneous problem. Electrolyte is present everywhere. So these are the equations that are valid anywhere in the electrolyte. Okay, whether they are, that electrolyte is present in the electrode, it is present in the separator, wherever it is present, these equations are valid. Okay, fine. Now, similar to the Fick's law that we saw in the last, in case of the electrode, let's talk about the how to relate the concentration and the flux in case of electrolyte. So then it is going to be N tilde Li plus is going to be minus D. Here I will write E. This I think we don't need to keep it as a function of the concentration that much. 1 second now. Minus dE del C, the concentration of Li plus, okay, plus overall plus, and I have T plus I E divided by Faraday constant. Let me just confirm this one. Mostly it should be right, but still, so that I don't tell you anything wrong. Yes, it's fine. Okay. Let me have you the, okay, this one is fine. Okay, so the first term is similar to electrode case, where there is a, due to the concentration gradient, there is a movement of the lithium plus ion that is happening. That is same as the previous case. There is the additional term. Okay, so here even if the concentration gradient is 0, there is going to be the movement of the ions, lithium plus ion, and that is due to going to be the electrostatics, or sorry, the electrical stuff that is going on, the amount of the charge, the current that is moving, right? So this T plus is known as transference number, which is generally given, okay, and it can be calculated experimentally. Okay, the typical value is around 0.35, right? And F is the Faraday constant, I is the current. Okay, so again we are able to relate the flux and all those things. Now the last thing that we need is how the I thing is there. So I E is minus sigma E, and this is del phi E, okay, plus now this is one I always forget, other things I remember. So this is slightly more complicated. Minus 2 by F 1 minus T plus and del mu E. This also can be written as minus sigma E del phi E minus 2 by F 1 minus T plus d mu E over d C E and del C E. Okay. So if you want, you can focus on the last one only, although the last one is also fine. So where the mu Anybody know? That is known as chemical potential. Okay. Again, we will not go into those much detail. This is the overall relationship. The main thing that you have to notice here is in case of electrolyte, the current is depend on the voltage difference, the potential gradient, as well as on the concentration gradient. Right. While in case of electrode, it was actually dependent only on the potential. I can actually go to the summary slide. Right. So we have done quite a bit of, this is the electrode equation, this we saw, right? This we know, the current charge conservation, this is the constitutive law, this is how the current is actually dependent on the electric potential. Again, electric potential you know, right, the amount of the work that is required to bring the unit charge, right? So this is what it is. Now this is the electrode equation, these four, these are the electrolyte equation. So del dot, this is the conservation of the lithium plus ion, this is the conservation of the charge, this is the constitutive law relating the flux of the positive ion with the concentration gradient as well as the current, and here the current is again related with the potential gradient as well as the concentration gradient. So this actually these four are the actually partial differential equation that you have to solve in order to simulate the electrochemical phenomena in the lithium ion battery. Along with this, two here and two here, four constitutive law. These are the equation that you need. Okay, fine. The main thing to remember here is, here the constitutive law is very simple, and the reason is, in case of electrode only the electrons are moving, while in case of electrolyte the things are much more complicated because the movement of the current is generated by the cation as well as anion. Although we are not going into the electrochemistry that much, but because of that the constitutive law underlying actually becomes much more different, more complicated, and the current is actually a function of the chemical potential also. So again, how the mu is rated with respect to the concentration, those there are some simple laws. The most simple is the assuming the electrolyte is the ideal, which assume that the overall concentration of the lithium compound is much lower, then that is actually has the mu here is mu naught plus RT ln CE. Okay, this is the simplest law that you can assume. There is a more complicated version of that also. So the chemical, ultimately the chemical potential is also a function of the concentration of the species. So these are the four equations, and if you solve them, then you will be able to simulate the electrochemical. Okay, so at least 60% or 70% of the story is completed. So I am just stopping if there is any doubt or comment. इसका so what it is saying, that the flux, there will be a flux of the positive ion even if the concentration gradient is not present. Okay, so because if this del C term is 0, then the concentration gradient is not there. That means everywhere the lithium plus ion concentration is uniform in the spatial domain. Then also there will be a flux of the positive ion, and that will be because of this particular quantity. So this current IE, that is made of two parts. Okay, that it is getting generated by the movement of the positive ions as well as negative ions. Now this T plus number or the quantity is known as transference number. Okay, so this T plus actually denote that how much of that. So if I say T plus is 0.3, that means 30% of the current is carried by the positive ions. Okay, if the T plus is 7.7, then the 70% of the current is carried out the positive ions. So this is kind of, if you say, one second. Okay. So this is kind of the current that is carried out the positive ion. And if you see in the denominator, there is a F, which is a Faraday constant. So that it, so if you have the amount of the charge that is carried out, if you divide by the Faraday constant, then you will get the number of the mole that is getting transmitted. Right? So that's why I am dividing by the, or we are dividing, not I am dividing, with the Faraday constant. Okay. So here the overall, there is a chemistry part that is actually playing because of the anion and cation. Right.
Is there any equivalence of the transparency of the heat transfer?
No, I don't think so. Yeah, even I don't think so.
In heat transfer, that equation will, the right hand side will only have the first term.
Yes, yes.
Second term is
Will not be, will not there. Oh.
because the amount of heat that is
Hmm,
does not
hmm,
depend on the absolute
hmm,
temperature, it only depends
On the grid. So this will not be there.
The second part is actually coming because of the generation of PL6 negative in the electrolyte.
There is, so because there is a negative ion that are there because of that. So even my electrochemistry is very like not that. No, I will not say great, not even good in that way. I just know the mathematical equation. So yeah, maybe chemical scientists can give a slightly better physical intuition than me in terms of answering this one. Okay. But yes, there is. So now once we have the equation, these are partial differential equation and those are time dependent partial differential equation. In order to solve this partial differential equation, what do you need? You need, the story is not complete only if you have the equation. You need boundary condition as well as initial condition. Here the initial conditions are fairly trivial. Main issue is the boundary condition, that is actually decently complicated. Right? These two are not independent. Right? One is in the electrode domain, another is in the electrolyte domain, but they have to talk with each other in some way. The lithium conservation of the lithium or the lithium concentration will depend on the lithium plus ion. Right now they are looking independent of each other. Right? There has to be some kind of talk that has to go between the electrode and the electrolyte. Right? So that actually goes through what is known as famously known as Butler-Warmer equation. Okay. So the Butler-Warmer equation, I don't know whether I should write it. It is already written here. I can skip the hard part and I can refer here. So, but anyway, let me show to the previous slide. One second. So this electrode particles are there, right? So if you see this boundary, right, at this, so this reaction, lithium is decomposing in the lithium plus electron. Everything is happening at the boundary between the electrode particle and the electrolyte. Right? So there is, on the boundary only they are talking to each other. Right? So this reaction that is happening, that is the one which is actually the main driver of the current. Right? If this reaction doesn't happen, the current is not going to get generated in the lithium ion battery. Right? So at this boundary, right, of the particle, there is a torque that is going on between the electrode and electrolyte, and that torque is actually quantified by the equation, the below equation, and this equation is known as Butler-Warmer equation. Okay. So what it says is the current that is flowing, okay, it depends on Jk naught, which is a constant, sine hyperbolic into f by 2 RT and eta k. So eta k is what is known as over potential. Okay, and the over potential is given by phi k, that is the potential of the positive electrode at the boundary. Okay, at the point that you are talking about, at the particular boundary, what is the potential? Phi k. What is the potential of the electrolyte at that particular point? And minus uk, that is the open circuit voltage of that electrode at that particular concentration, right? So although I have not defined the open voltage like when if you see for a define a open voltage for a battery, that is the voltage that is generated when it is almost not giving any current. Okay, so if you just connect the multimeter there in the battery without any load, then so phi k minus phi e minus uk, but this is not the open voltage for the battery, it is the open voltage for that particular electrode. Okay, that's why there is a subscript k. There is a jk naught, which is the constant, that is the in some way if the eta k is 0, this is known as equilibrium state, right? This particular over potential is 0, then this particular quantity sin hyperbolic 0 will become 1, and then you will get jk naught. Okay, so that is the current that is drawn if the in the equilibrium state, and right, and again you can derive it using this particular formula. Again, I don't want to go into detail of this thing, but this is how the, and this is a famous Butler-Warmer equation that is there, right? So yes,
What is the origin of the Butler-Warmer equation? Where does it come from?
I don't know. I think there is a, so in the electrochemistry, I think there is a what is known as equilibrium electrochemistry, and this is like more like a transient kind of phenomena. As far as I understand, in my limited understanding, even there is a lot of open question like how this kind of phenomena happen. Even there, the understanding of the like chemical people are quite limited. It is more, I think, the way it was given. It was more like empirical one. As far as I know, that is my understanding. Right? There is no, as per se, derivation. At least I have not found any derivation there. But this tells you that uh, as much the higher is the over potential, that means the higher voltage difference you apply across the battery for the charging, the higher is going to be the current flow, right? That much it tells you. And yeah, it is a slightly simplified version of the Butler-Warmer, but I think that is fine for this lecture. You can see sometime it is not 1 by 2, it is um, some kind of constant beta and then 1 minus beta, but I think generally typically we take it as a 1 by 2 only, so I think it is fine. Okay, more or less done, little bit more and we will be done with the stuff, right? So let's talk about all the boundaries, right? So we have two things, we have phi as unknown potential and we have the concentration, right? So we talk about this boundary right here, how the current is actually related. So current is relating what quantity? The concentration of the lithium. One second, I should have one question, or I have, yes, sorry, I forgot one more thing. So if you see this one, this is this is a Faraday constant. I can, one second. This is actually very sensitive. Okay. So at the boundary, you have the current that is flowing out, right? So that means if I take the current IK, take a dot product with the normal, then that will be equal to the JK current that is given by the Butler-Warmer, right? Because ultimately I want to, the quantity that I talked earlier was the current and the flux. So I want my boundary condition in terms of the current and flux, right? So the current is actually given by the IK dot NK equal to JK, and the flux actually, in order to get the flux, all you have to do is just multiply with the Faraday constant, right? Or actually you have to just divide. I don't know why this keep on popping up. हाँ अच्छा okay fine ठीक है, okay. And the similar thing on the electrode light side. And so this is about the boundary between the electrode and the electrolyte, but there is a more boundary, there is other boundary, right? And these boundaries are there at the here, right? So in case of here, the phi is equal to 0, the potential is equal to 0, right? The here you can specify some kind of potential, right? Or you can specify some kind of current, okay? Right? And that's it, I guess. I can talk about slightly more detail, but I think that is fine. Okay? So the only thing is you have to specify. This is also boundary, right? Top and bottom. So in the top and bottom, there cannot be a current going out. There cannot be a flux going out. So ultimately, at the top and bottom, it is going to be I tilde dot n tilde equal to 0 and n tilde dot n tilde equal to 0. That is going to be at the top and bottom. There is no current that is flowing out at the top and bottom. So the flux as well as the current, that is going to be 0. Okay, fine. Separator you don't need to model. So when you are modeling as an electrolyte domain, then it is actually automatically taken care. There is actually one point that I omitted, but we can talk about this boundary, because the positive electrode, whatever the equation that you are solving for, actually will talk about only here. So for the positive electrode, this also will be a boundary. So here you also have to provide the boundary condition, and those boundary condition will be actually the current I tilde dot n equal to 0, and apart from that the flux tilde dot n equal to 0, because at once you have reached the separator, all the currents is actually now taken care by the electrolyte. The electrode particles are no longer carrying the current, so that's why you take the this particular condition here at the boundary between the separator and the electrode. My battery discharge. No, so you can, I don't know, like those who want to see, you can just search this paper and go through it, and if you have any doubt, you can anyway ask me tomorrow or any day. Anyway, I will be here. So now this is was, but what is the issue? So if you see, whatever we have discussed is the most fundamental way of modeling the lithium ion batteries. Okay, so why not stop here? Why not actually go and again discuss something tomorrow? We can actually stop here, right? Because this is the most fundamental way of doing the things. So, but there is a lot of problem if we try to model whatever we have discussed today, right? The first thing, the problem is how I can make this nice looking diagram here. I can maybe make the electrode particle image even more fancier, but to actual battery, to get this image for actual battery, that is very difficult. That what is the actual distribution of the particle and everything. So it is a, so this information is actually very hard to get. One. Second, if these are not 8 or 10 particles, these are thousands of particles sitting sometime there. If I start modeling each and every particle, and these are non-linear partial differential equation, I have not gone into how do you solve it. Actually, you have to discretize each of the particle with the finite element mass, then you have to apply Newton-Raphson, and then you have to solve everything. You have to do the implicit time integration and all those things. We are not going there. So it is going to be computationally really a big challenge to actually directly model whatever we have discussed. Okay, so we want something which is slightly more practical compared to whatever we have discussed. So this lays the foundation of the all other model, but this is not that much practical in general to actually model everything. Okay, so that's why we have to know, or we want to know, the homogenized model, where we don't actually resolve individual particle and we try to average out the overall behavior and try to see that. Okay, fine. Okay.